And you need a reverse bias p-n junction because reverse bias p-n junction is depleted. There are no free charge carriers. And therefore, when this photon is incident onto this reverse bias p-n junction, it displaces off electrons from the valence band to the conduction band, and you have electrons available in the conduction band. So the number of photons that is incident onto this reverse bias p-n junction equivalently generates an equivalent number of electrons in the conduction band, and the number of electrons in the conduction band then becomes proportional to the number of photons. So you have a way of measuring the number of photons that is being incident. Now, once the electrons have moved from valence band to the conduction band, they are free to move, free to flow around, and therefore constitutes a photocurrent. And you need a storage device for this charges that has moved to the conduction band. So primarily you have capacitors which acts as a storage element. Now, fortunately, when you use a reverse bias p-n junction, you don't need a separate capacitance. The depletion region of the p-n junction itself come with its inherent depletion capacitance, and that depletion capacitance can, so this is the depletion capacitance. So this depletion capacitance can be used to store the charges that are generated from the valence band to the conduction band. So once you have the charges, this charges needs to be converted into a voltage, and for that, what you need is a buffer. So primarily to sense an electrical signal and to sense an optical signal and generate an electrical signal, what you need is a p-n junction, which is reverse biased, and a buffer. With this information, let's go and start designing a pixel. Just for the audience, if you don't follow anything, you're free to interrupt and ask me at that slide itself so that I clarify. If you just wait for a longer time, then might be the context is lost. So please feel free to interrupt me if you don't follow something. Okay. So this is how a pixel works. What you see is over here is a p-n junction. Now I want to reverse bias this p-n junction. Therefore, I use this reset switch and a V reset. So when the switch is closed, so let me close the switch. When the switch is closed, then this potential over here is V reset, which is higher. And that's what you see. The VDD or the VD, the diode potential is equivalent to V reset. And once the diode is reverse biased, the reset switch is open. So you open the reset switch over here. And once you open the reset switch over here, light starts to get incident onto the pixel. This generate electron hole pairs, and these electrons then flow through this capacitor and discharge this potential over here. Right. So this is how you see that discharge happens. Now you know that if there is a low light environment, if the number of photons in the environment is low, then the rate at which this electron hole pair generation will happen is low, and therefore the discharge rate is going to be smaller. Whereas in a very, very high light environment, the discharge rate will be substantially higher, and this is what you see in highlight cases, that the discharge rate is substantially higher. At what point should you measure the signal? Right. We define that point at which we measure the signal is call it as an exposure period. So exposure period is kind of a fixed time at which we measure the output voltage VD, and you see that the output voltage is substantially higher if the incident light was very, very high, whereas the output voltage is lower in case the signal photons was low in the environment. So this is how a conventional pixel works. In fact, all your mobile phones work with a very, very similar principle. You just have a p-n junction and a reset switch to reverse bias the photodiode. There are primarily two different types of sensors available in the market. One is a CCD, the other is a CMOS. CCD stands for charge coupled devices, and CMOS stands for complementary metal oxide semiconductor. In CCD, you don't use a p-n junction, rather you use a MOS capacitor, whereas in CMOS, you use p-n junction to detect the photons. CCDs primarily work in charge domain. You see that the charges that are generated because of the incident photons are transferred through each CCD element, and then you have the charge to voltage conversion happening at the last stage of the charge transfer, just near the output pad of the chip. Whereas in CMOS, you see that this is your pixel and you have transistors within the pixel, and therefore the charge to voltage conversion happens within the pixel itself. Now, naturally, if the charge to voltage conversion is happening within the pixel in CMOS, the noise level of CMOS is also substantially higher, right, compared to CCDs. So CCDs are very, very low noise devices as compared to CMOS. Fortunately, in the last decade or so, the performance of CMOS have drastically improved, and they are now compatible to that of the CCDs. If you look into the architectural viewpoint, the difference between the CCD and CMOS, you have lens, which is a common element for both the sensors. The color filter pixel array are also common. In CCD, the analog signal chain, the analog to digital converter, the digital signal chain are not on the same substrate as the MOS capacitors. So you have one die for CCD and the other die for readout electronics. So it's a 2-die solution. Whereas in CMOS, you have the analog signal, the digital converters in the same substrate, and therefore it's a single chip solution. Right. CCDs are now kind of obsolete, so we will not discuss about CCDs any further. CMOS are the kind of sensors that it has taken over for all imaging applications. So this is the pixel that I talked about, the passive pixel. You see that you have a reverse bias PN junction, right? And then you have a single switch to kind of reverse bias and transfer the data onto the column bus, right? The problem with this simple switch-based architecture, which is also called as a passive sensor, is that you have a column capacitance, and this column capacitance is substantially higher than your depletion capacitance, and therefore to transfer the information from the pixel to the column, you have loading effect, and this loading effect causes not all the signal charges to be transferred onto the column. To prevent that, what you introduce is a common drain amplifier, a source follower transistor, right? And this source follower transistor provides you with a high input impedance and a low output impedance, and therefore it disconnects the depletion capacitance from the column capacitance, and therefore the loading effect is taken care of. So this common drain amplifier, the source follower, acts as a buffer, which transfers. So this is the source follower, I'm sorry, right? So this source follower transfers the signal from the photodiode onto the column bus. Now, because it has a buffer in the pixel, it is called as an APS, active pixel sensor. And 3 transistor, because if you count the number of transistors, 1, 2, 3. So it's a 3 transistor pixel. You already know the reset switch is used to reverse bias the PN junction. The SF transistor is used to prevent the loading of the column onto the pixel, and the select switch is used to actively select a pixel. In a given array, let's say you have a 1 megapixel sensor, if you want to have actively control each pixel, then you have the select switch, which gives us selectivity in choosing a defined pixel. You have another variant of the APS called the 4T APS, and in 4T APS, what you see is that instead of a conventional PN junction, you have a P plus spinning layer, which helps to reduce the substrate dark current. So the substrate of a silicon is usually not very planar, and therefore it introduces a lot of noise. This PPD is actually helps in reducing the interface traps available on the surface, and therefore to reduce the noise. If you remember that this PPD structure helps to reduce the noise on the pixel side, that's good enough. And you have this extra transistor in the pixel. So there's a 4 transistor. The rest of the architecture is pretty much the same. With this, I hope you have understood how a pixel works. Now, for all imaging applications, there are some parameters which are of importance. And the first parameter that is of importance is called the dynamic range. And to help you understand what is dynamic range, I will take the help of a glass of a beer. If you have ever tried to fill a glass of a beer, you see that you can never fill the glass of the beer to the brim. You will always be able to fill to this level, and then the rest is a froth. In real optical environment, this froth represents the photon shot noise. Light will always come with its own noise called the photon shot noise. And therefore, if the size of the glass represents the depletion capacitance, right, because the depletion capacitance effectively tells you how many charges can be stored in the pixel. So the size of this glass represents the depletion capacitance. You see that not the entire glass can be used to store the photodiodes, right? A certain portion is always occupied by the photon shot noise, and therefore you have only till the saturation capacity. And the saturation capacity is actually defining the dynamic range. So often, if you think that you have a larger bucket, you can save more information. That is not true. Similarly, when you empty the glass, you see that it is very difficult to empty the last few drops of the beer, and that represents the dark noise. So the pixel can never be empty. Even if you try to transfer all the information from the pixel to the column processing circuit, you will see that there's always some components which is left behind, and therefore that represents the dark noise. In an effect, the dynamic range is defined as the saturation capacity divided by the dark noise, right? So this is what it is defined as. It is defined as the ratio of the maximum detectable signal to the minimum detectable signal. So as I told you, that as the incoming light photons are incident onto the PN junction, the current increases, and therefore the voltage discharge at the capacitor happens. And that's what you see is that the output voltage linearly increases, but it can only increase up to a level of a saturation capacity. And on the lower side, it is limited by the noise floor. And therefore, effectively, the dynamic range is limited by both the saturation as well as the noise floor. If you observe the dynamic range of commercial grade CCDs that are available in the market, you will see that the dynamic range is in the order of around 80 dB, whereas consumer grade CMOS, the mobile phone grade CMOS, they have a dynamic range of around 50 to 60 dB. And that's why for very high light and very low light, if you see that your mobile phones doesn't work properly, right? So these are the various shades that are available in the environment, from dark light, which is around 10 power minus 4 lux, to all the way to sunshine in midsummer, which is around 10 power 5 lux. You ideally want an imager with this high dynamic range, but that is not possible, right? Your eye can do that because your eye has a dynamic range of around 180 dB, but that is not possible with a conventional imager. And just to get a feel of how the dynamic range actually limits the imaging environment, you see this is a very, very high dynamic range scene, wherein this man is hiding behind a very low light environment, whereas this chair is in the sunlight, so it sees a very bright object. Now, if you do a very short exposure, so if you don't integrate over a long period of time, then you see that you can't see the man at all. The low light performance has become absolutely poor. If you do a medium exposure, then you are able to see this man, but the chair has started to become saturated, right? Because saturated practically means that there is no difference between the neighboring pixel information, and therefore you cannot distinguish the information that is available between the neighboring pixels. And if you have a very, very long exposure, then you see that you can see this man very, very clearly, but all this highlight scene has completely been lost. So you will not be able to see the things that are available that has a higher light, right? So to explain the integration time, if you have very low integration time, you get kind of a dark environment. Whereas if you have a very high integration time, then you see saturation in the image, and therefore you are not able to distinguish some of the features. So effectively, you need to have a a good dynamic range in order to image the low light environment as well as the high light environment. Especially in case of bio applications, you need very high dynamic range, because very often you will have very dark environment, and wherever you're using kind of phosphorus or photoluminescence, then you will see that you have a very light and peak time period, and therefore you need to also be able to capture or image in very high light environment. So your sensors that are used for biomedical application must have very high dynamic range. Coming to what are the popular HDR techniques that are available in literature, you see that you have logarithmic pixel, you have well capacity adjustment pixel, and I'll briefly describe these in the next slides. You have multiple sampling and the pulse frequency modulation pixels. That's for the highlight primarily, and for the low light you have charge multiplication and use of device called as SPAD. SPAD is for single photon avalanche diodes. So they are active, or they become active even in the presence of a single photon. They work in kind of a breakdown mode. Image intensifiers, and you have something called an electron bombardment. Let's go to one step at a time, one trick at a time. You see this M2 switch, which was used to reset the photodiode, the reset photodiode, is now kind of gate diode connected. Now once you gate diode connect this transistor, this works like a diode, and therefore the discharge on this potential is kind of logarithmic. So the conventional discharge would have happened like this. But now you see that because the discharge on this photodiode is logarithmic in nature, because M2 works like a diode, you see that the discharge happens like this. So in a conventional mode where the saturation is happening over here, you have delayed the saturation all the way up to here by making the M2 transistor work as a log pixel and as a diode, and therefore discharging the photodiode in a logarithmic way. This gives you an enhanced dynamic range. So you see that for a conventional photodiode, this was the dynamic range, whereas for this logarithmic pixel, the dynamic range has kind of substantially increased. However, because you have you have kind of connected M2 to a diode configuration, this node cannot be reset to the same level every time. You need to reset this photodiode so that you work this device in reverse bias mode. So this reverse bias potential will vary for every frame that you capture, which introduces its own noise and is not good, right? So it's slightly noisy, but helps you in achieving substantially high dynamic range. The other methods wherein you can increase the dynamic range is called as a well capacity adjusted pixel. In well capacity adjusted pixel, what you see is that you have the source follower capacitance on which you're dumping the charges. Once you short this, once you turn on the transistor M4, you see that you have gate diode connected the M1 transistor. Remember, M1 transistor is a source follower transistor, and therefore you have your CGD transistor. So the parasitic transistors of M1 are kind of shorted, and therefore it helps you to achieve smaller capacitances. And when you open this up, you have the parasitic capacitance of M1 coming into picture, which then adds up to your charge sense diffusion capacitance. And in a way, you have a way to increase the photodiode capacitance. And that's what you see is that instead of having a single capacitance, which would have given you the conventional signal like this, by kind of modulating the signal on various capacitance, you have slightly increased the dynamic range. So for the conventional, the dynamic range was this much, and for this modulated capacitance one, the dynamic range has kind of slightly increased. I'm not going in detail on the technical aspect to it. You can explore it in literature. I'm just giving you a feel of the tricks or the circuits that are available to increase the dynamic range for bio applications. You also have something called as a frequency modulation, pulse frequency modulation, and the circuit works like this. So this node discharges, and as this node discharges and becomes equal to Vref, So as VPD becomes equal to Vref, then the comparator toggles high. And once it's toggled high, then through a feedback signal, this photodiode is reset back to the VDD. And you know how many times you have kind of reset the photodiode. At the output, you combine the number of times you have reset the photodiodes. And based on that, you can actually increase your saturation capacity, right? For example, if this well can hold 1,000 electrons, then, and if you have reset 10 times, then you know that 10,000 electrons have been incident onto this photodiode. So this is kind of an indirect photon counting in which you measure the number of times the photodiode is reset, and you know that it gets reset for every 1,000 electrons, and therefore the 1,000 electrons times the number of reset gives you the actual photodiode well capacity, and that's a way of increasing the dynamic range, the measured dynamic range. You also have something called a charge multiplication. What happens in charge multiplication is that you have one electron hole pair generated due to one photon, and then you kind of pass it to another bigger well and apply a very large electric field. And because you have applied a large electric field, this electron, photon generated electron, will gain in energy and bombard with neighboring electrons to generate more photoelectrons. So this is an avalanche breakdown that happens. And if you repeat this process of avalanche breakdown multiple times, then you get a substantially large signal. An analogy of this is simple as to how you cool your coffee in South India, right? If you have a hot coffee, then you just simply juggle between two glasses, and then there is an adiabatic transfer of heat, and that's how your coffee cools down, right? So the same thing happens over here. You have one electron, and you juggle between two wells, providing a very high electric field, and this electric field causes an avalanche breakdown, and this breakdown produces more electrons from this single electron generated due to the photons. And once you have an impact ionization, you have a larger photons, and that is also helping you to detect low light environment or to detect low photons, and therefore to enhance the dynamic range in low light signals. A similar device that you have in literature is a SPAD. SPAD stands for single photon avalanche diode. So SPAD, you see, this is a reverse bias characteristic of a photodiode, and SPADs actually work in a breakdown mode. Most of your camera sensors work in the linear mode, so they work here. CMOS sensor work in the linear mode, so it works here, whereas SPAD works for the breakdown mode, so you bias the sensor over here, and when one photon gets incident, even a single electron hole per generation produces a very large current, and this large current then can be detected by your radar electronics, right? So SPADs are generally used in an environment where you have very, very low light. So this is some of the works that I've presented so far are the works in the literature, and these are some of the works from IIT Delhi. So this is our work. What we also did, so this you see over here is a conventional pixel, and this is a source follower. We kind of modulated the capacitance of the source follower to produce different well capacitances, and these different well capacitances also helped us in achieving very high gain for low light, and I will show you some of the images. So this was the sensor array that was kind of fabricated. This is the microchip that you see that was fabricated. So this was fabricated on a 350 nanometer AMS opto process. And these are the test bench and the test structures to test this pixels designed. And what you see is that this is the conventional exposure versus output plot, right? So this is the saturation over here. And here you see a kind of a read noise floor. We were able to increase the sensitivity of the low light substantially. So the conventional one starts from here, whereas in our case, you see that already from here, you have the signal valid. So it's kind of increase the performance in low light. Picture talks 1,000 words. So this was a kind of a cartoon, which was not being able to image in a normal light environment by a conventional photodiode, a conventional camera, whereas in our sensor, we were able to image the edges very, very nicely. And not only image, we were able to saturate in the same optical condition. So the optical condition, the light environment was substantially lower. However, we were able to produce a significant gain in the pixel, which helped us to achieve a substantially better performance. The pixel so you see that the saturation is limited by the size of the photodiode, and the noise floor is limited by the component noise. So the pixel has a lot of components. It has photodiode, it has reset transistor, it has source follower, it has select switch. All of these transistors contribute noise, and this noise is what limits the lower floor of the dynamic range. Right, because the dynamic range is the ratio of the saturation to noise flow. If somehow you can reduce the noise flow, then you can get a better dynamic range. And to see an effect, how does this pixel and the column noise actually affects? You see that pixel to pixel there is a variation because of the noise that is present in each of the transistors. Similarly, column transistors, a column also had processing logic, and the column processing logic also has additional noise sources. So effectively, an image that you read out from a conventional CMOS pixel is very, very noisy. And a standard trick to reduce this noise is a correlated double sampling, CDS, in which you sample the signal twice and subtract it so that whatever offset that you have and the reset noise that you have gets eliminated. Right. So that has been applied in most of the imaging sensors, and the thermal noise component is pretty well eliminated. However, this buffer source follower over here, this buffer over here, introduces a low frequency noise, introduces a 1 by F noise, and by 1 by F noise does not lowers in the presence of a CDS. So if you do CDS, the source follower low frequency noise does not go down. It actually increases. So you cannot use CDS, you have to use something else. What people use to reduce the noise of the source follower is something called as a switched biasing. So instead of keeping the source follower on all the time, what you do is you turn on and off the source follower. Now, if you turn on and off the source follower, the noise that is available in the track charges are released when the transistor is off, and therefore the probability that the noise electrons influencing the signal is very, very low. What you see by simply switching on and off your buffer, you see you're simply switching on and off your buffer. And if you switch on and off your buffer, then your source follower moves between inversion and accumulation, and that helps in almost 6 dB reduction in the noise power. So we had this switch in our pixel. So what we did was, instead of turning on the source follower continuously, we kind of modulated the signal and operated the source follower in switched bias mode. Once we did that, what you see is that this is an image, and you see the noise in the image. This noise is composed of both the thermal noise as well as the low frequency noise. When we do CDS onto it, you see that the thermal noise is gone, right? And when you do switched biasing plus the CDS, you see that effectively it is noise free. And when you apply a gain to it, you see that you obtain a very, very nice signal. Now these signals are all raw images coming out of the image sensor. They are not digitally processed signal. There's no MATLAB algorithm that has been applied on this. These are direct digital signals coming from the sensors that we have designed. You are free to apply your algorithmic skills onto it and make the images more beautiful. So in our algorithm, you see the conventional sensor was giving us a noise floor of around 24 electrons, and that we got it lowered to around 2.3 electrons. So these are some of the further studies where we kind of took the source follower and modulated the source follower. Yeah. Hello? Hello? Is there any question?
You can continue, sir. I think some disturbance.
So you can modulate the source follower in a pulsed manner, right? You turn on and off the source follower, and you see a substantial reduction in the noise flow, right? So this is when the source follower is not switched on and off, whereas when the source follower is turned on and off and with a varying duty cycle, you see a substantial reduction in the noise flow. You can also reduce the noise flow using chopping. Chopping is a very commonly known circuit trick, wherein you have a baseband signal, you modulate the baseband signal to higher frequencies, and then you introduce your noise signal, noise and offset, then you down modulate it, so your signal comes to DC, whereas your noise goes to higher frequencies, and then you apply a low pass filter to recover your signal and get rid of your noise and your offset. We did some work on chopping, wherein we introduced chopping in the pixel. So the circuit that looks is pretty complex. However, not going into the circuit, you again see a conventional photodiode and a conventional source follower and a select switch that you have seen before to read out. We had to introduce an extra chopper switch to chop the signal in order to reduce the 1/f noise of the signal. And these are some of the measurements of the chip that we fabricated. You see that there is almost 6 dB reduction in the noise when we chop the signal. Images are more useful in analyzing. You see that when we don't apply in-pixel chopping, you see the salt and pepper noise that is clearly visible, and also the random variation that you see over here. So these are the random variation in the pixel output. Whereas when we do in-pixel chopping, you see that the image is pretty clean, and also you see that the variation in the pixel has substantially lowered. The variance in the pixel has kind of substantially gone down. And these are some of the images that we have captured. So this is an image from a mobile phone, right? And this is with a very, very low integration time, and this is the very, very high integration time. And we measured that the low frequency noise was kind of substantially lowered, right? So in this part, I've kind of talked to you about some of the circuits that are available for high dynamic range, which you absolutely need for many biomedical imaging applications. The other part, I'm going to talk about two other aspects to imaging. One thing you might be wondering is how do you obtain color imaging in most of these imaging sensors. So just let me briefly introduce as to how you get color imaging, because so far I've shown you all monochrome images. Silicon is basically monochrome, right? It can't differentiate between a red photon and a blue photon. For that, you need something else. And let me briefly introduce you to color imaging. So you see that as your color increases, your wavelength increases, your photon energy goes down. Your photon energy is given by hc by lambda. So with increase in lambda, your photon energy goes down, right? Further, what you see in human eyes, you get color visions because of the cones that are available. The rods gives you the black and white vision. However, the important thing to see is that the rod peak sensitivity and the green peak sensitivity are close by, right? Please remember these two data. We'll use them. How do pixels detect color? Because silicon is primarily monochromatic. Silicon cannot differentiate between a blue photon and a green photon. Therefore, what you actually need is kind of a filter. For example, I will use a green filter, and this green filter only allows the green photons to pass through and rejects blue and red photons. So this primarily tells me that color imaging is bad in low light environment, because in color imaging, 2/3 of the photon is lost, and therefore you will see that often the cameras that are made for low light imaging are monochrome in nature, because in low light environment you have very less number of photons, and therefore you want to capture all the photons available, and you don't want to lose 2/3 of the photons because of the color filter present. A standard way of obtaining color filters is to use a Bayer array, and Bayer array is simply a repetition of a blue, green, green, red filter. So this is a 2x2 array which is repeated over the entire imaging array. You can ask me why 2 green, why not 2 blue? 2 green because you saw that the rods and the green cones have nearly similar peak sensitivity, and therefore our eyes are very, very sensitive to green light. And to mimic or to give a better perception to our human eyes, the conventional photodiode sensors also have 2 green filters so that the image is more greenish in nature. So if I use the Bayer filter, so then you see that 25% of the filter is red, so you will see kind of an image which looks like this. 50% of the filter is green, so if you only image the green pixels, you see something like this. 25% of the pixels are blue pixels, and this is what you see in the 25 pixels. And if you kind of add them, then you get a kind of a mosaicing image. And this image is not good, because if you want to sell a camera which gives you an image of this kind, then nobody is going to buy that camera, right? So what you need to do is demosaicing, and demosaicing is what is done in normal cameras too. So you have an imager where you get an image something like this by combining the red, green, blue pixels. You want something like this from the left hand side. So what you do over here is that the green pixels that you have, and you want to find the intermediate GX, where you have a kind of a red filter. So GX can simply be taken as an average of G1, G2, G3, and G4. Similarly, between the red pixels, you have a green pixels, and the green information in the red pixel can be obtained by averaging the neighboring red pixel data. And similarly, you do it for blue data. This is a simple averaging and interpolating the data. And now, if I take the same red pixels and interpolate the red information for the green and the blue pixels as well, then you get an image which looks like this. If I do it for green, blue, and if I combine it, then the image looks beautiful. And then this is what you want to buy. If your camera is able to give you this kind of images, then you will definitely buy them. There's another aspect to imaging which is now becoming very, very popular in biomedical imaging. It's called polarization imaging. And I'm going to talk about one work that we have done at IIT Delhi, is measurement of heart rate and SpO2 non-contactly. So what you see is that you have the skin, and you have the veins and the arteries underneath the skin. If you incident a polarized light, then the superficial and the deep reflections are going to be completely different. So they are going to be in phase completely in a different manner, right? So the deep reflections will be more unpolarized. So you have incident on a polarized light. So the light that is coming from a deep layers will be highly unpolarized, where the light that is coming from the superficial layers will be kind of slightly more polarized, and therefore you can easily distinguish between superficial and deep if you are able to measure the polarization aspect of it. How do you measure the polarization in a conventional camera? You can't detect a phase using a standard CCD or a CMOS. They can only measure intensity. As I told you, they cannot also measure color, and therefore you need this color filter. For polarization, you need presentation is in presentation mode. Okay, so polarization, you need this polarization filter, right? So you need this polarization filter, and this polarization filter helps you if you have an unpolarized light incident onto it, then this unpolarized light passes through a polarizer, and one phase polarized light is then incident, which is then converted into an intensity by the pixel array, right? And that's the only way of detecting a phase information by a CMOS image sensor. So you see some of the images that are captured by our face cameras. You see that the certain pixels which are dark, while certain pixels that are white. This is because there are linear array on top of the pixel, and you will follow it once I show you how this imager is created. So we put a fingertip onto the in front of this polarization array, and based on the polarized information reflecting back from the fingertip, we were able to analyze the SpO2 data. Now I'll show you some of the results. So these are the micropolarizers, and this is how the micropolarizer array is created. So these are the pixels. These are single pixels, and you see that these are small arrays in which the transmission axis of the polarizer can vary, and based on different transmission axes of the polarizer, this micropolarizers are kind of placed on top of your pixels, and that gives the polarization sensitivity to your imaging array. So if in order to distinguish between p polarized and s polarized light passing through this grid array, you must satisfy that your lambda by d, the d is the pitch of this grid, must be much greater than 2, right? So this array must be satisfied. This condition must be satisfied only if the incident light is unpolarized, then the reflected or the transmitted light will be polarized in nature. So what we did, we used the metal stacks of a CMOS. So this is a CMOS, right? And every CMOS has a metal stack which is used to do an interconnection between different transistors. So we use the metal stacks. In fact, we use the metal one to create a wire grid. So this is the wire grid that we want to have a polarizer. So we used a metal one to create a wire grid on top of your photodiode, So basically you have this 4 pixels. So 1, 2, 3, and 4 pixels, and you see that we created a different transmission axis. So in the top one, you have 2 pixels, which has no grid, and therefore it is measuring the intensity. Whereas in the other two, it has kind of a horizontal and a vertical grid, and therefore it is measuring the 0 degree and 90 degree polarization. And the third array, we also have a 40 degree polarizer, which tends to detect the 40 degree polarization information. Does this architecture detects polarization? We did some extinction measurement tests. So this is the transmission photograph, and you see that here in this region there are no metal grids, no wire grids, and therefore you see that there are the intensity is measured. Here you see only 2 metal grids, and therefore you see only kind of one column which is kind of dark, because this metal grid will attenuate 50% of your light. Whereas in the third part, you have 3 metal layers, and therefore you see a larger attenuation of light in this region. A polarizer is measured using the transmission profile, and you see that we do get the transmission profile for 0 degree and 90 degree, as well as for the third part, we also see a maximum at 45 degree, and this is what is expected. The Malus law says that for 0 degree polarizer, you will see a peak at 0 degree, and that's exactly what it is seen. So Malus law is kind of verified. So these filters, this array acts like a polarization filter. What you see over here is some of the measurement results from the sensor. So we place our fingertip and incident unpolarized light onto the fingertip, and the reflected polarized light or unpolarized light was then measured using our polarization sensors. And what you see is that I deep and I superficial. So you expect that I deep is more unpolarized, and therefore the variation in I deep is going to be substantially larger. And this is what you see, that the variation in I deep is substantially larger compared to I superficial. And from I deep and I superficial, you can actually kind of estimate your SpO2, and you see that you have a linear variance in SpO2. We measured, we referenced our data with respect to the conventional SpO2 sensors available in the literature, and we were able to achieve better performance. Mind you, this is completely a non-contact device, so there was the sensor was far away from the fingertip, whereas in most of the SpO2 measuring device, the device is practically in contact with the fingertip, right? So the contact devices are not so good, because if the hand movement occurs, then it introduces a lot of motion distortion, whereas these non-contact based sensors are kind of free of motion blur or motion artifacts. Further, because it is measuring phase information, and it is actually measuring a ratio of phase information, the color of the skin also does not influence the measurement result drastically, which is a severe problem for conventional SpO2 and heart rate monitoring device. Some of the other experiment that we did with this phase measurement sensor was to actually see whether we can predict the degradation in a fruit, degradation in an apple. And we took 2 different kinds of apple, red star and also the green one, right, Granny Smith. And you see that we measured the phase information over time, and some of the results were kind of very interesting. With time, you expect that the apples will degrade, and that's actually what your phase information shows. So S0 is Stokes first polarized Stokes information, and Stokes information is used to kind of quantify the polarization state of the reflected light. And you see that for all cases with passing time, the polarization state degraded. That pretty much mean that the reflected light, as the apple degrades, as the apple kind of becomes rotten over time, the information, the reflected phase information that is coming out varies, and based on the reflected phase information, we can actually predict the health of the apple. In many cases, you will also need to measure the depth in bioapplication. Also, you will need to measure how far is your skin contact or your blood vessel from your skin surface. Polarization sensors can also be used for time of flight based applications. In time of flight based applications, you have a light source, it strikes the object and it is reflected back. And you know the speed of the light, you know the time at which the light was emitted and the time at which the light is detected by the sensor. And from these two information, you can actually calculate the distance of the object from the sensor. And these are some of the experimental results that we did, wherein we were able to predict the depth information very, very accurately. This, we did it in a lab environment, but we can also do it for bio applications. Right. So I think I'm over time. I think I need to finish. So this was my last slide. This is also just to show that when if three objects were placed at three different distances, and our polarization time of flight based sensors were able to very accurately pick the distance between the three objects very nicely, right? So these concepts that I talked about, the high dynamic range, the color filtering, and the polarizations are pretty commonly used in biomedical imaging in both terms of spatial and high temporal resolutions, right? So I think my time is also up, so I will stop here, and if there are any questions, then I'll be happy to take them now.
Thank you, sir, for wonderful presentation. If any question, you can directly interact with the speaker. Sir, one question from my side.
Yeah.
The pixel noise you are talking about now, sir.
Yes.
How it is going to affect in power dissipation, sir?
So usually, in order to keep the pixel noise lower, you have to burn more current. So if you want your source follower pixel noise to be low, then you have to bias that with a very large current, right? And therefore the pixel power increases, right? The power consumption increases. If by using circuit architectures like chopping and other architectures, if you're able to lower the pixel noise substantially, then you do not need to burn more current, and therefore you save in terms of power.
Thank you, sir. So one more, sir, you're talking about HDR techniques.
Yes.
So is there any drawback?
There's no drawback, but the one limitation that you can have is that most of the cameras that you get in the market either work for low light or work for the high light, right? There are very few cameras which actually work for very low light as well as very high light, because those needs very large full well capacity, right? So there you have so most of the cameras, high dynamic range cameras that you kind of procure, they will be limited in terms of their performance. They are they will not work. Let's say if they are working very efficiently in high light, then they will not be very efficient in low light.
Thank you, sir. Thank you very much.
Sir, I have a question.
Yes,
This
please.
is Prabhavati.
Yeah, please go
Hello.
ahead. Yeah, please go ahead.
Sir, HDR
question?
itself is a high power consumption or the
No.
concept. And how can we make it low
But-
power here? And another thing is, in normal SPO2 devices, though they are not in camera based or anything like that, we measure other parameters also, like not BP,
Right.
the pulses,
Yeah.
rate of pulses and other things. So is that possible with this also?
Yes. So let me answer your first question first. So HDR is high power. That is not correct. HDR, this high dynamic range images, are the most of the cameras that you buy off the shelf in the market consume high power because the way that HDR images is generated. In HDR, what they do is they capture low light information first, then the highlight information, and they kind of combine those images. So there is a lot of processing that is happening in those HDR cameras. So basically the processing power is substantially high, and that causes the HDR camera to be very high power. Now, if you have very high sensitivity in the pixel itself, right, then you don't have to do a lot of FPGA processing. And if you don't have to, if you don't need your FPGA processing, then the power consumptions are not going to be substantially higher. It's going to be considerably lower. Still, you have to see how to obtain a single shot. So more of the dynamic range images that I've talked about, somewhere single shot. So in one shot, you get full HDR, right? Some sensors were kind of multi-shots. You have to take 2 or 3 different shots and then combine the images to obtain a high dynamic range, right? Wherever you have multi-shot and combine the images to obtain a HDR, those will be slightly power hungry. But if you do it in sensor domain, if you do it in analog domain, then the power consumption is substantially lower compared to when you do it in digital domain, right? The second
And
question.
another thing is, sir, I agree that processing that means power consumption, this thing. Can we fix up the resolution, whatever that is required for the measurement, and then restrict the power here?
Yes. So many large format imaging sensors give you an option to work in ROI based readout mode, right?
Yes,
So
yes.
if you work in ROI based readout modes, so for example, if you have a 10 megapixel sensor, you might not need 10 megapixel every time, right? So if you need just 1 megapixel, so you use a 1 megapixel ROI and read it, because you're not activating the other 9 megapixel pixels, right? The power consumption will be substantially lower, right? However, there are different aspects to power consumption, right? It's the power consumption of the pixel, the power consumption of the column, the power consumption of the frame, right? At what speed you're operating, if you're operating at 30 frames per second or you're operating at 100 frames per second, all those defines the power. So basically, if you want to go lower in power, spatial resolution is one thing, but you also have to see the temporal resolution as well as the noise, the optimal readout of the column, because all column readouts are kind of designed at a minimum readout speed, right? Minimum power. So all
Yes.
those optimization also needs to be done if you want to kind of reduce the power.
Okay.
Your
And the
second question,
second
whether
part
this
is,
whether the device where I showed SPO2, in fact, our published paper in IEEE sensors, we have also shown that heart rate can be easily measured. Heart rate, we can also have this PPG, right? So I just showed over here that SPO2 measurement is more accurate, but the heart rate was also very accurate. In fact, we kind of benchmark with the commercial oximeters that are present, and the oximeter variation was almost over 15%, whereas our data measurement was less than 5%, right? So heart rate, PPG, all those things can be measured. We were now actually exploring if we can also measure the sugar content, the blood glucose content in the blood. So that also we're exploring. Because these are non-contact devices, right? And there's a place far away from your imaging sensor, there is a lot of environmental noise that comes into picture, right? Or ambient light, which tends to kind of saturate the photodiodes, right? So there's a lot of ambient noise comes into picture. So we need to kind of individually take care of these noise and then kind of work on the very low intensity signals that we get, right?
yes.
But based on the processing, yes, it is indeed possible to get more information.
But do you think because of analog processing that the noise is going to be a problem? That is whatever ambient noise and other things. If we have taken the digital noise, because ambient noise is going to be at one level and we can always recognize it and filter it off.
Yes,
if we employ digital processing. So you think
in
the
fact,
limitation is only because of analog processing?
in fact, let me make a statement that it is much more easier to eliminate the background light in analog processing compared to digital, because in digital you have to read the entire frame,
Okay.
right, to do your subtraction. And if you have a 1 megapixel imager, then you're reading 1 megapixel image to take out your background light, right? We have our work published in TCAS 1 in 2000, I think 2019-20, wherein with a single capacitor in the pixel, we were able to reduce 120 kilolux of background light. Right.
Oh, okay. Okay.
So that is much more easier.
Yes,
That's much
yes.
more
The
easier to do in analog
frequency
domain
domain.
compared to digital.
Okay. I got it, sir. I mean, it didn't strike in the first. Thank you, sir.
Thank you.
So any other question, participants? If no, thank you very much, sir, for your informative presentation. We'll resume back at 11:30. We'll take now for the tea break. Thank you very much.
Okay. Thank you, Jalajaji. Thank you, everyone, for attending.
Thank you.
Okay. Thanks. I will log out. Okay.
Where we'll be giving you an overview of VLSI designs and the coding techniques. And the coming 2 days it will be an offline session. So to start with, we will take you through the applications in medical domain from the coding perspectives and from the material perspectives, as well as physical design on 3D ICs. So as this workshop is focused more into the biomedical applications, we'll be just seeing what are the different coding techniques, and with respect to the materials, how we can design these biomedical systems. So in the recent advances in integrated circuit technology, as well as innovation in circuit design techniques, which have led to the systems with processing capabilities that can supplement or even entirely replace complex biomedical applications or operations. But however, with the right technical approach, this functionality can be achieved at power levels and form factors, allowing these systems to be entirely implantable. For example, if I take an implanted medical device which was powered by a low power general purpose processor, which consumes approximately 10 milliwatts, current battery technology would accommodate approximately 3 days of operation. Alternatively, dedicated solutions employing specialized low power design techniques consume approximately 8 microwatts. So we can achieve like more than 10 years of operation with the same battery. So ASIC, as we know, plays a very important role in the medical domain. So coming to the integrated circuit trends, I think all of us know it is nothing but an entire circuit on a single piece of silicon, first which appeared around 1960, and with the increasing technology and all, these gates became more complex, and hence we had this SSI, small scale integration, and medium scale integration, large scale integration, and ultra large scale integration, etc., etc. And in the picture we can see the number of transistors with respect to the years. It is keep on increasing on a single piece of silicon. So what exactly or how exactly is an IC created? So in short, I can tell it is nothing but the design, manufacturing, and test. Test also plays a very important role. Hence, the design is based on the specification, what comes at the end. The end customer, based on their specification, we try to do the design, and based on the design, we try to manufacture, and finally we get a VLSI chip. So when I say about the VLSI chip, it is nothing but a packaged one got from the foundry, and after getting it from the foundry, we call it as a full chip, which goes for testing. So of course there are many types of tests once it comes out of the fab. So depending on the test patterns and the vectors generated, it will go to different types of bins. One is the fail bin and the pass bin, and intermediate also will be going. So that can be used for some other application where these patterns are not critical with respect to whatever application we are doing. So hence we can see here during shipping we'll see whether it is the chips are passed or failed. And we have a company here, Tezol, which will do the testing of the chips, and we can easily see how the bins will be segregated with respect to the good chips and bad chips. And of course, when we are doing the testing and all, yield comes into picture. Hence, when we are doing these testing of the chips, many things come into picture, which we'll be seeing in the following slides. But why VLSI is so important? I think from day very long, we have these chips for communication purpose, we have chips for smart homes, and we have chips for robotics. And now we have these chips for medical applications, which are becoming very, very crucial. So to reduce healthcare cost while simultaneously delivering high quality health services, we need to develop a new portable or implantable biomedical devices, which is of great importance. And hence we can save billions of dollars by reforming today's healthcare infrastructure with these medical devices for various applications like health monitoring. Where when I talk of health monitoring, we can see the health condition, or we can say health condition should be reliably monitored for each person to predict and diagnose chronic diseases at very early stage. For example, ECG signals can be continuously measured and automatically classified by portable biomedical devices, for example, to diagnose irregular heartbeats, etc., etc. And we can also see with respect to the clinical treatment. So your clinical therapy should be reliably delivered for each patient for both preventive care and disease treatment. Then we need to also see, when I say to achieve these goals, our biomedical device must accurately generate the desired output. And we should also look at the latency of the device also. That is, the response of the medical device must be sufficiently fast for a number of real-time applications such as vital signal monitoring and deep brain stimulations, etc. Then we should also see that whatever the device, it should be of low power, as those chips will go into the human body and we cannot expect the power to be more. So each time when I stress, I always stress about the cost, portability, and reliable. So to facilitate a portable, or I can say an implantable device to continuously operate over a long time without recharging the battery, its power consumption must be minimized, especially for the implantable applications where power consumption is highly constrained. So hence, it is necessary to design an ASIC circuit instead of what we call as the general purpose microprocessors or programmable devices such as FPGAs to meet these tight power budgets. And we should also concentrate or focus on the flexibility issues also. That means reconfigurability is also needed to customize a biomedical device for different patients or at different usage scenarios. So hence, I always think that in biomedical domain also, these chips play an important role. Next, coming to the design methodology, any design can be decided whether it can be with respect to a top-down method or bottom-up methodology. So we can see the block diagrams with respect to the top-down design methodology or bottom-up design methodology, where in top-down design, we realize the desired complex behavior of a hardware by partitioning it into an interconnect of simpler sub-behavior, and hence we create lower level of abstraction from the upper level. So we go from upper level and then come to the leaf level or a leaf cell. When we come to the bottom-up design, this aims at realizing the desired complex behavior by suitable selection and interconnection of parts, components from available set of parts with some known behavior. It also creates abstraction from the low-level behavior. So as we can see, from the leaf cell, we try to go to the top-level blocks. But if you want to go for good designs, we need both top-down and bottom-up efforts. So again, that depends on the application, whether we want to go for a top-down or a bottom-up approach. Next, we also have the design styles, where broadly it can be classified as full custom ASICs, semi-custom ASICs, and programmable ASICs. Where when we talk of full custom ASICs, we see that all the cells are customized and all the mask layers are also customized. I always take to this example of a kurta when we buy from a mall. If we have to make it for our requirement, what we do is we just take the material and go to a tailor and get it done according to our requirement. So when it is done according to our requirement, we say that it is fully customized. That means it exactly fits to our own cells. Most of these analog blocks comes under the fully customized design. When we talk about the semi-custom designs, we can see here all logic cells are pre-designed. So when I say pre-designed, some of them are already available, whereas some of them we can make it work to our requirement. For example, the same kurta, maybe we need to stitch the the sleeves, etc., etc. So we can say that some of them are pre-designed, which are defined. We can take it from the style library, whereas some of them we need to customize it to our requirement, and hence we have these examples like standard cell-based, and we also have this gate array-based ASICs. I will not touch upon deep into this because we have other things coming into picture. Then we have this programmable ASICs, where we have all the cells are pre-designed and none of the mask layers are customized. So these are typically PLDs and field programmable arrays. But the problem with these PLDs and field programmable arrays are the resources are all limited. So when I say the resources are limited, we cannot, in the sense to say, if I talk of a full custom, we have no standard blocks and we have control of the full design. But we also get the best results, but the design cycle time is very slow and we can only have our complete design. So all analog blocks and all comes under full custom. But when we use the semi-custom, we use the cell libraries from the vendor, and hence the design cycle time is faster and all digital ICs are designed like, for example, DSP blocks, etc. So when we come to these programmable logic devices, all digital concepts is nothing but sum of products or product of sums, and hence everything will boil down to these expressions. And if you want to do it by using PLD, we have something called as the PAL-ASM, where we can program these according to our requirement. But the problem with PLDs are we need to use the whole of the devices, and hence the power dissipation will be more. And when we have to go for a huge complexity, PLDs will not be that much useful, and hence we're going for FPGAs, where we program using these gate arrays. There are different types of structures in our FPGAs, which we'll be dealing with later on, and how do we code when we want to program for FPGAs or ASIC will be dealt in the afternoon session. So PLDs or FPGAs, we'll be just doing the prototyping, and when we want to go for large production, we'll go for ASIC. So ASIC is nothing but application specific integrated circuit. So when I give an example, it is like when we go to a mall, we just see a dog barking. Inside that will be a small IC which will be done for that particular application. So if you want to devise any medical devices, we need to have the small ICs which will be sitting inside our human body, and what are the different factors to be considered when we are devising such ICs will be dealt in the coming days ahead. So when we do a comparison of these full custom standard cell and gate arrays and as well as FPGAs, we'll see the full custom plays the design cost is high, but the other things are variable, and hence for analog devices or analog blocks, we can go for full custom, whereas for the digital blocks, we can go for the standard cell, gate arrays or FPGAs. Of course, for FPGAs, we always go for prototyping and then go for ASICs for mass production. So this is just a comparison to show that what will happen to the cell size, cells type, and the placement of the cell with respect to the interconnection, as well as the design cost, which is high with respect to full custom, and the others are okay with respect to the cell size, cell type, cell placement, and interconnection. So when we do with respect to the comparison of these with respect to area, performance, and fabrication, the choice of the design style also plays a major role, and time to market and the total number of chips to be manufactured also plays a role. So hence, full custom designs are used for microprocessors and other complex volume applications, whereas FPGAs are used for simple and low volume application. But we can always mix these. Sometimes we also use IPs also to release our chips to market at an earlier phase. So and again for large circuits, it is common to partition the circuit with smaller sub-circuits, which will be designed using different themes. The reason being is, suppose from ARM we get the direct IP, and from Intel we just get the processor core and all. So finally, when you try to make it as a system on chip, then again the design styles vary with respect to each team. So all that will be decided when we are doing the design at the top level approach or the bottom level approach. So this gives a comparison. When the complexity of our design is small, we can just download on the Spartan 3. Whereas if it is huge, of course we have to download where the other blocks are there, which supports for various processing application. The latest what we are using there is the zinc board, and of course with the differences lies with respect to the technology and with respect to the logic cells and how many flip-flops we can configure, and the memory blocks with respect to the DSP blocks and also the IO pins. So each one will be enabled for different applications. So how we want our medical devices, we can just download on the FPGA and see whether it is working fine before going for that particular application. And I'll just show you a short video of how these chips are made.
What we need for the sake of convenience called a chip is officially called an IC, or abbreviation for integrated circuit. A chip is like a city with no people but bustling with activity. The chip is packed with industrial buildings, control centers and powerful components such as transistors and resistors, which together form one huge network. The chip's data structure flows vast amounts of fast traffic along roads and communication networks. The building blocks and chips are not only becoming ever smaller, but our designers are also making the chips clever over time. so as to create more possibilities continuously. This makes the equipment controlled by these chips better, safer, easier to operate, more energy efficient, and friendly to the environment. Let's try these 7-minute boots that are various process by means of which products such as chips are produced at Philips Milwaukee. They explain aspects such as the most important steps in the production of ICs, and to make this easier to understand, we have developed a series of animations. A chip is an extremely small silicon plate, ranging from a couple to several dozen square millimeters in size. This tiny silicon plate is then filled up with a great number, sometimes millions, of microelements such as transistors, diodes, and resistors, which together form an integrated circuit, the IC. We make a large number of chips all at once on a round silicon disk called a wafer or slice. First of all, we create a layer of silicon on the slice, 1/100th of a millimeter thick. We then oxidize this silicon layer in an oven, so that an even thinner insulating layer is created on top of it. We then apply a coat of light-sensitive lacquer. We expose the lacquer through a kind of photographic negative, so that the lacquer dissolves in certain places. Then, in the places where there is no more lacquer, we shoot atoms with great accuracy through the oxidized layer into the silicon. The layer of lacquer is then no longer required, and is therefore removed from the slice. We then ensure that the atoms penetrate a little deeper into the silicon by a 4/1000th of a millimeter. A more silicon layer is applied over the oxide layer. And once again, a layer of lacquer is applied, exposed, and developed. The silicon which is uncovered by this process is then etched away. Another series of treatments involving lacquering, exposure, environment with atoms which penetrate the silicon, more oxide layers, etc., is performed until the whole pattern is complete in all its layers. Some 300 to 400 process steps are required, along with 15 to 20 different tasks with microscopically small patterns. The final step in the process is the connection of the various, almost invisible, tiny elements in the silicon. This is how you make an electronic circuit, an IC or chip. Naturally, we have a particularly good relationship with our suppliers, as they obtain their part in determining the final quality of our products. Silicon is made from ordinary quartz sand, and lots of silicon have been created for drilling at extremely high temperatures. These slices have been sewn up into rods with great accuracy. The ICs will be produced on these slices of silicon, for which purpose the slices will undergo 300 to 400 processes. The first step in the production process is as follows. In a special oven, the slices are covered by a more thin layer of very pure silicon, into which the transistors and other components can be built. The slices with a monomer silicon are placed in other boxes, where the silicon is allowed to oxidize. This insulating oxide layer can be removed at a later stage when necessary. These are known as VLSIs. Here, extremely intelligent, fully automated machines are used to apply the light-sensitive layer of lacquer to the oxide on the slices and to expose the slices. No light is used in these rooms, as the lacquer is not sensitive to this. The patterns on the masks, a kind of photographic negative, are of course designed by our own development engineers. The techniques themselves are made by other specialists. It goes without saying that we also cooperate very closely with the suppliers and equipment manufacturers. In the lesson called in-90s, specific atoms can be shot into the unprotected areas of the silicon to give them a positive or negative conductivity. This is done incredibly accurately. For example, one atom in 100,000 silicon atoms. One of the next steps in the process is etching, removing material locally from the slices with great accuracy. This department uses an automatically controlled process involving acids and caustics. Another technique used is dry etching with an etching gas. This picture gives an impression of the technology involved in this dry etching. All the process steps we've seen, and many more, are repeated until the product has been fully assembled. This is what the smallest parts look like through a special electron microscope. Sometimes, the chip designers use a technique in which the chip is sewn through, so you can even look inside. The last step in the process involves making connections between the various elements in the silicon. These are so tiny that a minuscule vacuum-deposited layer of aluminium is required to make them. The innumerable processes, which take approximately 3 weeks to complete, are completed by an initial visual inspection. Each chip is checked for a number of essential functions. After testing, chips which do not comply with the specifications are marked with an ink dot, so they will no longer be used. Once they've been tested, the chips are ready for assembly. First of all, the slices are laid on a layer of adhesive film, and the layer is sewn through in 2 directions by a special, amazingly accurate sewing machine, so that the chips are always separated. The slices are then carefully packaged and sent to their service centers in the Far East: Bangkok, Hong Kong, Manila, and Kaohsiung in Taiwan.
Okay, this was just a glance of how chips are made. from one of the companies. So now we'll start with the ASIC design flow and the way we design electronic circuits with respect to deep submicron. So when we are talking of deep submicron, we'll be thinking what actually is our technology node. So previously it was, we were talking of 180 nanometer and now it has gone up to 3 and all. So what exactly is happening is, when we talk of the feature size of any semiconductor technology, it is defined as the minimum length of the MOS transistor channel between the drain and the source, and the technology has been scaling year by year. So when I say scaling is nothing but reduction of size, and if double number of transistors can be incorporated on the same area, it means it gets approximately double the functionality for the same cost. Alternatively, with scaling of technology, the same functionality will be available at roughly half the cost. And moreover, smaller the channel length, faster would be the transient response of the transistors, which would translate into better performance. So the goal of every design company now is to double the number of transistors on their integrated circuits with each technology. So as we can see, from 180 nanometer, we go up to, industries are going up to 3 nanometer, and this is what about the scaling, which just represent the characteristics of any technology and will just represent the length between the source and drain of a MOS transistor. And while manufacturing any die, I think on Wednesday we'll be showing you the wafers. So we will see the dies in the center will be pretty accurate in the process value, but the ones lying in the periphery will try to, or will tend to deviate from the values. So the deviation is not that big, but it can have a significant impact on the timing also. So we will see all this on Wednesday, face to face, what are these wafers and what are these unfinished dies and all. So now as we can see, the basic or the ASIC design flow, which will start right from the spec, and when we go for the low power techniques, we have to start right at the specification level itself. As we know, there are two kinds of powers need to be looked into, the dynamic and static or the leakage. So dynamic power dissipation can be affected by the following factors, that is the VDD, the material used, switching, short circuit current, clock gating, then operations such as isolations and all. So we will see all this one by one, and when we are doing this, we will see the clock frequency is also increasing with a continuous increase in the number of transistors on chip. And when we are implementing low power technique, especially for these designs, we have to see that these low power techniques are being implemented across all level of abstraction. That is from system level to the device level. So here there are many approaches which are related to front-end HTL based design styles, which I talked about, and which can reduce the power consumptions. And also power dissipation, which has a direct relation with the clock frequency, and dynamic power also depends upon the rate at which the data toggles for a given circuit. So as we have discussed the design styles and all, we will focus on several areas of designing using HDL, which are many times not that significant as they do not affect the functionality. So we will see what are the guidelines to be mentioned to simply implement low power blocks and all. As we know, leakage power can be optimized by multi-VT or power gating, and power also depends on the supply voltage. So by reducing supply voltage, power dissipation can be reduced. But decreasing the supply voltage again tends to increase the delay. And finally, we have to, the balance has to be created, and we use level shifters and all. Either it can be low to high or high to low. And power also depends on the material used to fabricate the IC. And we have so many new technologies like silicon and insulator, which helps in power optimization. But the major component, as we see, power dissipation is due to the switching. That is transition of signal from high to low and vice versa, which causes the capacitance to charge and discharge. So the dissipation is huge during this cycle. And depending on the rate of the transition, short circuit current also contributes to the power dissipation. And this kind of power can be optimized by ensuring minimum switching, which can be accounted for at the architecture level. So we will see how that will be done in the afternoon when we try to tell in what way are the design excellent coding styles which can be done at the architecture level to help in the power reduction. So based on the specification, we try to go for the design entry. The design entry can be written either in Verilog or VSGL. So here, when I talk of the coding, we should write a RTL code. So when I say an RTL code, that means it is a synthesizable code. So synthesizable code is nothing but all the data blocks will be between two register levels. So when I say RTL, it is an HDL, but not all HDLs are RTL. So industry always prefers for the designers to write a RTL code. So after writing the RTL code, previously we used to do some linting checks and all after the synthesis. But now to check the quality of the code based on the coding practices, usually based on some guidelines, we do the linting check. The tool will do before simulation once our RTL is ready. So now after this one, we'll do the linting check. Why? Because after synthesis and after DFT, if you do, again there will be a time loss, and hence to see all that, this is checked once the RTL is ready. So once the RTL is ready, we'll do the functional simulation. So functional simulation just tells, for example, AND is an AND gate, but the gate delays are all not considered when we are doing at this level of verification. So of course, when we do the synthesis, we'll just see how the gates will be transferred to that particular technology. So whatever we write the code, whether it's maybe in Verilog or VHDL, it will be just mapped to that particular technology with respect to the gates. I'll just touch upon briefly. So when we are after doing the synthesis, we will do the partitioning of chips so that whatever given at the input crosses all the blocks, and finally we get the outputs properly. Then when we do the design for test, DFT, which was not that much taken, but now DFT has become a lead role, especially in case of the medical devices. The reason is we need to identify the fault chips before it goes to the test phase. Why? Because again time to market should be very less, and hence we need to identify faulty chips before it goes to the field, and can be simplified if the chips are designed for testabilities also, and hence now all the chips comes with DFT features. Next we go for floor planning. So floor planning is nothing but we need to plan the blocks the way it has to be arranged. Then we need to place that with respect to the blocks which need to communicate to each other, so that if the blocks are placed far off, again crosstalk comes into picture because we'll be working with respect to low power. Then we also have this CTS, that is the clock tree synthesis. This I always relate to with the flat in Bangalore. will have a water tank, and that water goes to all the flats. Similarly, your clock ring synthesis, depending on the type of clocks different to different blocks, applying the pressure, the main clock will have a clock generator, and that's get distributed to all the blocks. So again, depending on what type of structure we want, we will do the CTS. Then after the CTS, when we are doing at the synthesis level and all, we are not bothered that much about the clock. Why? Because we are just seeing whether the slack is met. Whereas when we come here at after placement and floor planning, we do the CTS to check whether all the blocks are working at that particular frequency. Of course, the tools will be taking care of all this. As I said, we have UPF format with respect to the synopsis people and CPF with respect to the cadence people. So based on that, since it is at this level, the tools, most of the things will be handled with respect to our VTs also. Whether do we have to have a multi-VT or low VT or high VT, again there is always a trade-off. Then when we come to the routing stage, there are different types of routings which we'll be discussing, that is global and detailed routing, and finally it goes for verification. So when it goes for verification, there's a huge difference between the verification and testing. Again, that is research on its own, and then it goes to, we give to the fab, which gives us the bitstream pattern, which will not be in a position to analyze that. Only the fab guys will be in a position to see what exactly we want with respect to the bit patterns. There are of course many foundries now, so previously there was so much of issue, like we need to wait, and if you miss that, it would take long hours to again get our chips done. But now because of the number of foundries are more, I think the time to market of those chips are happening fast, and I think Modi ji is also planning to have a foundry in Bangalore. We are hoping to have that so that all of us can have our own chips designed for that particular application. So there are many ASIC related companies worldwide. As we can see here, the colors represent where all we have these companies, right from Google up to Samsung. Of course, with Philips also, many Intel is also going for healthcare chips, and the technology trends in nanometer with respect to the decreasing lithographic size that is measured with respect to the gate length. So there are more specifications with respect to the lithography, that is nothing but the resolution. That is the smallest feature that can be printed. Then we have this pitch also, which relates to the spacing between the features. Then the alignment accuracy of the layer with respect to the previous layer also plays a major role. Then the wafers that can be processed per hour. Then if there are any defects, if they are generated on the wafers, then all these comes in the lithography process, and because it is deep sub-micron, there are so many challenges to be addressed. We have many companies in chip designs, right from software and hardware, and also foundry. So more number of companies in these chip designs, and hence opportunities are also there. Then with respect to the tools and all, we have many tools with respect to the front end and the back end, along with the power analysis tools. So we can make use of all these tools such that we can get a proper chip out, and hence hopefully if we get the bit patterns, we can get the chip outs from any of these foundries. Of course, many of these foundries are helping us to get the chips, provided we give the bit streams and never skip their deadlines. Then what are the main ASIC design challenges when we are going for these medical devices? One is the design challenges, as previously told, the frequency And with respect to the logic levels, then we have multiple clocks pitching in. And previously all the blocks would be on, but now that cannot be the case because the chips get heated up. Then we have timing closures, then we have still low power methods with respect to the nanometer technology. And when we are coding, we have to see whether if we are giving to the vendors, whether it is designed in Verilog or in VSDL, and how to make it as a mixed one. So that comes as the challenges in the front end part. So when we take up the back end part, again STS plays a major role because we need to see whether it has met the timing requirement. We see whether the timing of a design by checking all the possible paths if there are any timing violation. To debug these timing paths plays a very important role, and hence the challenges most come in the STA. Then layout, we need expertise in the layout also, because layout is like the way we arrange our things in the house so that crosstalk gets reduced. So we need timing experts, then the layout experts, then design experts. Of course, if you want to make our chips come out fast, we can have our DSP IPs from some company, and again when we try to merge with our blocks, there might be some timing issues, and when we try to put it in the layout, again problems may arise. Then with respect to power, we will start working on low power design, so we need to perform low power checks, as I already mentioned. UPF and CPF formats are there. We need to check upon these isolation cells, 11 shifters and retention cells, etc. Then, of course, DFT has to be done. Again, with respect to the patterns what we generate, we again have to see whether these patterns will generate power when we are verifying those patterns before it goes to the field. Then we also need to have this script expertise, because each time just with our Unix or Tickle will not going to help us. So we need to be flexible when we are dealing with scripting. Because for huge designs, as the complexity is huge, we need to do everything in the form of scripting languages, and again that becomes a challenge as the technology nodes shifts to the lower nanometers. And the latest ones is with respect to the packaging trends, where we can stack all dies, and we'll be seeing tomorrow the 3D ICs, the physical design, practically how it is happening and what are the challenges. And of course, we have these 3D ICs and 3D transistors, along with GAS, which is gate all around. If it is, the meaning is the gate is placed on all four sides of the channel, so that compared to the others, we get more efficiency, and hence people are heading towards the 3D ICs and GAS. So again, when we try to verify our designs, we have our codes and your system log for verification and the UVMs, which are all based on the IEEE standards. And when we talk with respect to synthesis, we have the libraries coming into picture, and we have different kinds of libraries, the logical libraries, which have only the relevant information such as area, timing, power, and functionality of these standard cells and IOs. Then we also have these simulation libraries, which contain timing and functional information for post-synthesis. Then we have symbol libraries, which are used to view the schematic of the generated netlist. We also, these are also known as the logical libraries, which are provided by the fabrication house, which is nothing but the collection of standard cells with their logical synthesis information. So typically it will be in the .lib format. For example, if I say a logic library, it will be a .lib. When I say a physical library, it will be .plib. When I say a schematic library, it will be .slib. Synthetic library, .sldb. And of course, our very long module file will be always .v. And we have the technology files where the libraries consist broadly of these standard cells and environmental variables, and also the library level attributes. For example, the time unit, the voltage unit, the capacitive load unit. I think all these practically, if you check, will be coming to know what all would happen, or the attributes which are defined in the library to model the variation in the environment, which consists of 3 parameters. That is the PVT, the process, voltage, and the temperature. And these can be operating on more than one operating condition, and typically like a minimum, max, and typical. And there are set of operating conditions defined in the library to specify the process, temperature, voltage, and the RC3 models. So these are used during synthesis and timing analysis of any design. And as we know, library developers may define any number of operating conditions in the library, and library is characterized using one set of operating conditions. But when we talk of this PVT, the process, voltage, and temperature, we should see that it will always vary from 0 to 1, and the voltage variation will depend on the technology being used, and the temperature varies normally between 0 to 125 degree centigrade. And of course, the other things also come into picture, like the wire load models and all, which I will not tell in detail, like the operating conditions, like worst, nominal, and best and all. We need to fix those values like process so much, temperature so much, and voltage so much for low power designs and all. And wire delays, of course, wire load models also will come into picture, and all that. When we do practically, we can just see how these wire load models and all vary with respect to the design and all. We have something called as the segmented and enclosed valve, which we need to give it in the tool. So we'll be seeing all that later on. Next, the coding styles also will be touched upon in the afternoon for low power designs. So as we can see here, the same process continues: the design entry, the synthesis, the place and route. And we need to, I'll talk about the metal fill later on. Then after the extraction, that is the parasitic extraction, there will be a timing sign off, and the chip will be released to market. So as we can see here, the different physical design flow, that is from RTL to GBS2, the design synthesis, the place and route, the placement, the CTS. We need to do the routing, and finally the chip finish for all these. So as I was talking, we need to do the floor planning properly, otherwise we will be getting many issues after the chip has been released to market. So we need to check all this. As you can see here, in the area given, we need to fix different modules at particular places. This is what has been shown here just from one of the students who was working on this. So we need to fix all those blocks properly and try to avoid as much as possible the crosstalk effect, especially for low power designs. Then, as I told, when we are placing, when we are doing the placements of these standard cells, we see that if one block has to communicate with the other block, it's always better to keep or to fix those blocks very near to each other, so that they can talk without any delay and no congestion, etc., which comes after the chip is been done. Of course, the standard cells, as I told, LVT, ULVT, SVT are all there, so which are directly picked from the libraries and will be doing the placement. Then CTS also. So we need to calculate what will be the when we try to capture those waveforms at the launch edge and the capture edge, what will be the setup and the hold time if there is a metastability issues coming into picture. Then whatever, especially in medical domain, whatever is the data we have to set at that time, it will not happen with respect to one clock cycles, since this is very crucial. We have to take care of these metastability issues. Then we need the physical connectivity with respect to the wiring. How do you do the track alignment? So when we do the track alignment, there is something called as the global routing and the detailed routing. And this routing problem is typically solved using two-step approach, that is global routing. As we can see here, global routing defines the routing regions and it generates a tentative route for each net. So when we assign, each net is assigned to a set of routing regions, and this does not specify the actual layers of layout of the wires. So as I said, it will just generate a tentative route for each net. Whereas when we talk about the detailed routing, for each, we can see here, there's a difference here. For each routing region, each net is passing through that region is assigned a particular routing track. So the actual layout of wires get fixed. That is, the channel routing and the switchbox routing and all get fixed at the detailed routing. So this is the main difference between the global routing and the detailed routing, whereas global is a tentative route for each net, whereas detailed, which will give us the actual layout of the wires and get fixed at this phase. Then when previously DFM was also not there, design for manufacturability, as we can see with technology, even a small hair that link gets cut, if there is any shock, what is happening to the layers, all these will become an issue at the time of DFM, that is designed for manufacturability. So the metal slotting in the higher layers, then you have this metal fill header. So whether performed by the designer or by the foundry, metal fill is a mandatory step at advanced nodes to ensure manufacturability and high yield. Of course, if there are more chips out in a good bin, then we'll get a high yield. If there are bad chips compared to the bad chips are more, then our yield is very low. So we always have to see our yield is very high. So when we are doing this metal fill, what is that means? It involves filling the empty or white spaces near the design with metal polygons to see that we get a regular planarization of the wafer. That means ups and downs should not be there. And foundry mandated fill requirements also will stipulate that the fill density will be within the specified minimum and maximum parameters. So we should see that the wafer should be even and smooth, not too many ups and downs. So while these regular plenarisms is crucial, we need to like when we are doing this polishing of these signal roots, these metal fills should not have other effect like sometimes timing may be an issue. Why? Because of this routing, we may get the capacitive coupling, increased capacitive coupling effect, which can disrupt to the nearby nets also. So the designer must ensure that the metal fill is done without impacting timing critical nets, and in other words, the fill needs to be timing aware. So timing awareness is also needed when we do this engineering change order, ECO, which arrives late in the design cycle, and this requires the designer to change the layout in case if the fill has affected as if there is any fill around the affected areas also during this ECO, we need to fix this one. Thus, like as we see, the fill methodology should also allow us to easily remove and reinsert these fills without violating any timing of the nearby nets, which is a major concern. So we need to fill the design while we need to minimize the capacitive coupling. These foundries also will respond with some increasing or sophisticated requirements to achieve the required fill density. So all that I think I can just tell this. Okay, like to tell metal fill is also a concern, and of course antenna fix that will come into the analog. I will not touch upon that. So when we need to physically verify, we have this DRC and LBCs and all. They should always be clean before we give a commitment into silicon. And after that, like for example, depending on the technology, we'll be having some specification with respect to the width and spacing between the each blocks. All that has to be satisfied to give a final pass at the top level modules. Then when all this is done, we do the extraction and timing sign off, and we get the tape out. So as we know, our main we can generalize a biomedical device which just includes or some components which will include data conversion. Then we can have the signal processing, and we'll be having some communication subsystems where these interface with the biomedical environment through sensors and actuators. So this is all these are small, very less components compared to the entertainment chips and all, and hence we see that so the techniques which require ultra low energy operation for doing some practical biomedical systems has to be taken care. And I think I will be ending this because we'll be having more on whatever I have told, hands-on and some more practical approaches in the coming days. So we can see some of the projects to be handled in the academics. We can have our low power RTL coding, which will be discussed in the afternoon to get a synthesizable circuit. As I told, RTL is an HDL, but not all HDLs are RTL. So when we write all this, we can implement an FPGA. Then we can have the layouts. We get free student version tools where we can try out with like respect to the low power. Then we can there are some spice simulation tools also. Then the most challenging is in the 3D ICs, which will be dealt tomorrow. And of course, we can have some EDA algorithms because when I say when we write the code in Verilog, we will be using only behavioral modeling. Why? Because many of the algorithms use behavioral modeling, which will be dealt in the afternoon to touch upon how to write efficient RTL coding. Then also materials also will touch upon how to go about for a biomedical device. And I think I will end for now. That's all from my side. Thank you.
Ma'am, at what time we can start, ma'am? Any question from the participants? If not, we'll take for the lunch break. At what time we can start, ma'am? Hello?
If there are no questions, then can I quit, madam?
Yes, ma'am. Can you hear my voice?
Hello?
Hello?
Hello, madam?
Ma'am, can you hear my voice?
Hello?
Hello? Hello? Hello? Hello.
One second,
Ma'am, can you hear my voice?
here. I'm Namita here. He is speaking, but one second.
No. No, done. It's not coming. Hello?
Hello? Hello? Hello? Hello?
Hello.
Hello? Yes, madam?
Ma'am, can you hear my voice?
Yeah.
So we'll take for a lunch break, ma'am.
Sure.
So at 2 o'clock we'll resume back.
Yeah, sure. Thank you, madam. So I'll do quickly.
Thank you very much.
Good afternoon. Am I audible?
Yes, ma'am.
Thank you, ma'am. I'll share my screen once. Is the screen visible?
Yes, ma'am.
Yes. Okay. So as ma'am said, we'll be starting with the introduction to Verilog or just an overview to Verilog so that we can design various digital circuit needed for the medical electronics or in medical applications. So to just start with, today we'll be giving an overview, just a brief introduction on Verilog, different styles of coding of digital circuits in Verilog, how to simulate it, and then on Wednesday we'll be seeing the same thing, codes hands-on using model sim. So to start with, we'll be using Verilog. Now in morning we have a discussion on various VLSI design styles that includes FPGA and ASIC. Now when we start any complex circuit for any medical application, we need the target device to be either fixed to FPGA or ASIC. To design on the using FPGA or ASIC, we need some CAD tools, and the CAD tools will understand one language so that it will be easy for us to design the digital circuit, and that is nothing but the Verilog. There is one more HDL language, that is VHDL, that is understood by an CAD tool so that we can design any circuit on FPGA or an ASIC. So here we will be using the HDL, this Verilog HDL that is used in both academic as well as it is industry common. VHDL is other common HDL that is used to design digital circuits. Whatever principle we'll discuss here will be common to both the VHDL as well as Verilog. Only the syntax will be different. Otherwise, the hardware wise, both are same. So when we talk about HDL, we should think hardware. It means we should always think hardware first and then start writing the codes. So to start, it is a Verilog that was developed in 1984 by Philip Morby, and it was a property of Gateway Design Automation that was acquired by Cadence in 1990, and then only the Cadence released it publicly. After that, then Open Verilog International was formed to control the language specification, and then it was acquired by IEEE, which released this Verilog HDL as IEEE standard 1364 in 1995. So Verilog IEEE standard is 1364. Now Verilog module, we'll start with the basic building block. All Verilog codes or any digital circuit, when we are designing it using Verilog module, it should start as module and end with AND module. Module followed by module name followed by port list. Then we have port declaration, parameter declaration, assignments, procedural block, instantiation of lower modules, task and functions. Example, we'll just go through an example of the same thing. It says we are writing for a decoder. It is a 2:4 decoder. So it says module. Here module is a keyword. followed by module name. As it is said here, it is a module name. It is decoder underscore 2 underscore 2 underscore 4. This module name is an identifier, that is, it's a user defined name and it has its own rules. It's not a keyword here, it's a user defined name. The rules, according to rules, it can contain alphabets, one special character as underscore, and the number, but it should not start with an underscore or numbers. It should start only with alphabet, followed by the port names. Port name says here A and D. As it is a decoder, we can say that input is 2-bit input and output is 4-bit. So when we write here port names, so we should write all the ports which will communicate with the outside world, whether it is input or output, should be defined in this port name section. After this, it is says that we have to define the type, which type refers to, like, what is A and what is D here. So A is of type input, it means we are reading the signal inside our design. D is of type output, it means we are assigning the value through our coding, and that is the output. So we are using the keyword input and we are using this output A and D. Now what is this 1:0 and 3:0? This is the size of our input and output. It can be a single bit or it can be more than 1 bit. If it is a single bit, we'll just write input A, output D. Since it is the more than 1 bit, we are just defining it as input 1:0 A, output 3:0 D. Then this is the module contents. It can be using any data style or any coding style. This is just an example of data flow that we'll see later. So this is the part where we define the functionality using one of the coding style or one of the programs. There will be various way to define that will contain here, and then end the design with end module. Again, this is the keyword. So whatever is underlined here are the keywords like module, input, output, assign, and end module. All other things are defined by the user. So when we say something, we'll just have description of keywords and identifier. So we can see all the keywords should be, when we are used to define the module names, port names, signal names, should be self-descriptive and they are in lowercase. Self-descriptive means you should give the name such that it defines the functionality of the signals or the modules. Then declare the signal connected to, choose same here, choose the descriptive signal names, choose the descriptive signal names for internal signals or writing the internals of the modules. Now declaring the ports. As we already said that ports will define the signals or the ports which communicate with the outside world, that is which interferes with the outside world. We have 3 types of ports available in Verilog: input, output, in-out. Input, what we can read; output, what we can assign. In-out means bidirectional, we can read as well as we can assign. Now each port can be of scalar, that is it can be of single bit, or it can be a vector, that is it can be of a multiple bit. So if I write input Cn, it is single bit. If I write more than 1 bit, I should define the range, what is the size of the port, and that is how it is defined. It is from MSB to LSB or LSB to MSB, that is we can write output 7:0 as out or 0:4 as in. You can even write 0:7 as out. So we should define the ports, defining the size of the ports while putting in this bracket, square brackets. After that, then we have various port list. So multiple ways to declare the ports of a module. One way, it is just like write the module, then write module name followed by all the ports, and then we will define the type, that is whether it is output or input or in-out, using the keyword input, output, in-out. After that, or the other way is module, same name, but it is like we are defining the port declaration as well as port together. That is output cout, comma sum, comma input A, comma B, and then end module. So here in the first, we are defining the ports and then defining the type. In the second way, we are defining the port as well as their type together. Any one can be used when we are writing the. Then this is with the size. These two things for the single bit. Now when we have more than one bit, it is the same way. We can define the ports first and then define the port types with their size. That is, out is of 8-bit, A and B are also of 8-bit input. As long as the size of the inputs are same or the output is same, we can define it with in the same line with comma. But when the sizes are different, we cannot define it together. Similarly, here in the second style, we are defining the ports as well as port types together. That is output 7:0 out, input 7:0 A comma B. Then we will go into the styles of coding. Styles of coding mainly broadly classified into three types, that is structural, RTL and behavioral. In that, structural means where we use some lower modules or the already inbuilt primitives from Verilog. When we design complex digital circuit using these modules and primitive, we call it as a structural. When we use some continuous assignment, we call it as an RTL or data flow. When we use initial or always block, we call it as a behavioral. A single module can use more than one method, but here first we'll see what are the differences between them. I'll just give you the brief introduction with one example. Later, we will see the details of the structural and behavioral data flow in detail. So now, for example, I have to design this a majority circuit. In this, inputs are V1, V2 and V3 and the output is measure. It says that when the number of bits, that is V1, V2, V3 are 1, majority is 1, then the output is 1. Otherwise, it is 0. It is the circuit for that. So using structural, we say we will define it using the connections of primitives. Primitives means already inbuilt gates available in Verilog. So here what we wrote here is module majority, same thing output input. Some internal net should be defined using wires, and we are doing it using the primitive, that is AND gate. So A0, A1, A2. Syntax of structural modeling, we'll go through it after completing some basic rules of Verilog. So we are saying and 3 times we are calling and we are calling one OR gate. If this is the style used, we call it as a structural modeling. The other thing remains same, start with module, end with end module, followed by module name, module name. Majority is the module name. This is a user defined name, followed by ports, port declaration, and then the designing part. Then we have the data flow style. Data flow style where we define how the input or flow from input side to output. We are just defining the flow of the inputs using some Boolean equation. So again, same thing, module name, ports, port types. Then we use assign, measure, and we are just writing this module equation or the Boolean equation using Verilog operators. This is when we have use this way, we call it as an RTL or data flow style. Then we have behavioral, where we define the behavior of the design functionality using algorithmic way. We are not worried about the structure. In structural, we were knowing the gates. In data flow, we should have the information of data flow in terms of Boolean equation. But here we are just writing if V1 and V2 or V2 and V3 or this thing is 1, then it is 1, else it is 0. So when we know the algorithm functionality, we go through the behavioral modeling style. This is one of the highest level of abstraction, or this is one way of design. This style is the highest level, as we are not restricted to any hardware. We are dependent on the synthesis tool to generate the hardware for us. Now, basic language rules. Verilog is case sensitive. Keywords are in lowercase. No space is allowed inside an identifier. As I already discussed, identifier is a user defined name. It can contain alphabets, numbers, and one special character underscore, but it should not start with an underscore and number, and there should not be any space when we define an identifier. Maximum of 1024 characters can be there in an identifier. First character not a digit. Statement has to be terminated by semicolon. If you are writing a string, it should be in double quotes and must be on single line. To comment the line, single line, we can use 2 slash. To comment multiple lines, we can use slash star and end with star slash. Now Verilog supports 4-value logic system, that is 0, we say normally for the false value, 1, we say it for true value, unknown, when we don't define anything properly, there is a lack of initialization, then we say it is unknown, X. Then we have Z, that is high impedance, when nothing is driving the signal. We say whenever the input is floating, we say it is Z. There is nothing at the output, is not connected to anything, we say it is high impedance. So X is due to some lack of, as we already said, lack of initialization. It is a conflict. We don't want any X in our design. So we should design, while writing codes, we should design it properly. So we should not get any X or Z unwantedly. How to represent a number in Verilog? Verilog numbers can be represented using size, tick, base, followed by number. Here size define the number of bits in the number, regardless of this base. The number of bits in this given number. Base define the base of the given number is specified in which base the number is specified in. It can be decimal, hexa, octal or binary. We'll write D or D for decimal, H, small h or H for hexa, O for octal, and B or capital B for binary. So you can write anything over here. Then number, it is the actual number in the given base. Now when we say size is a decimal only and represent the number of bits already discussed. The default size, if we don't represent size, it is 32 bits. The default base here is decimal. If we don't represent any base while writing the number, we'll take it as a decimal. So size default to at least 32. But you should always specify the size explicitly, otherwise it will create unnecessary 32-bit register if needed only 5 or 6 and may cause compilation errors on some compilers. Now when we say this number, if I write 4 tick D3 in the design, it can be read as 3. In decimal, obviously it's 3. In binary, since it is 4, it will be taking it as 0011. 3 tick HA. So decimal it is 10. Since here we gave size only as 3 bit, it will not be reading as 1010. It will be reading only as 010. It will truncate 1 bit. And we'll be reading only 010. 8 tick O26. So in decimal it is 26. In octal it is 10110 in binary. And since we specified size as 8, we'll be taking an 8-bit register and we are reading it as 000101110. Similarly, if we write something as 5 tick B11, in decimal it is 7, and when we extend it, when we are reading in binary, it is 111 with 0 padded because it is 5 bits here. Now same thing in this example, but if we see this example, 8 tick BX11001, we gave only 5 bits here, that is X1101. So extension will be X. So numbers with MSB of X or Z extended with that value itself. It will not be extended with 0. Other than that, if there is no X, it will be extended with 0, as we saw here. Tick 07, default size, since it is 32, it will take 32 bits. So 111, all remaining bits will be added with 0. Then it is just 10 means default base is decimal, default size is 32. So in decimal it is 10, it is not 10 in binary, it is in decimal 10. So this number will be equivalent to 000001010. Like that, we'll be reading this single 10. This is what with the basic rules of Verilog. Now we'll be starting with Verilog data types and operators. Physical net data types. Every net, whatever we are declaring, has a type associated with it. All ports are implicitly declared as wire or the net data type. Net is nothing but that represent connection between hardware elements, and they are declared using the keyword wire. Even we can write input wire A, output wire B. Like that, we can, each net by default is of type wire here. It does not store the value, therefore need to be continuously driven, and driver is implied when a net or drive, when there is a net or wire. It is equal to Z when it is not connected. Now we have various types of net as wire, WAN, WAR, tri. In this, wire is synthesizable, WAR and WAN are not synthesizable, tri is also not synthesizable. So wire, and by default all types of nets are wire type. So if we say wire, if I write wire Y, it is same as writing output Y. Assign Y is equal to A and B. So we can declare wire as this thing. Now if we write something as WAN Y, then if I write assign Y is equal to A, assign Y is equal to B, so it will be wired and. So when we are giving A and B as 0, 0, we'll get 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. Similarly, if we write something as war Y, it will be 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. But WAN and WAR are not synthesizable, hence it cannot be used for designing purpose. It can be used somewhere for the simulation purpose. Now the something is called as tri, if nothing, if direction is 1, it is A, else it will be Z. It says it is high impedance. We are any net declared as tri means by if nothing is driving that net, it will be read as Z, that is high impedance. Then we have another abstract register data type, that is one was net type and the other one is abstract, that is register data type. Register data types are the variables that store values, and the registers are declared primarily with this keyword reg. This declaring something as reg doesn't mean that in hardware we are getting flip-flop or real hardware, like hardware that stores value, that is registers, latch or flip-flop. But yes, reg can be used to generate latches or flip-flop. A register may be assigned, and whenever any net declared as reg can be assigned value only within a procedural statement, that is always an initial, a user defined primitives, a task or a function. Register cannot be used with assign. It cannot be used as a part of output of a primitive gate or a output of a module instantiation. That's why it is never can be assigned a value through a primitive gate output or a continuous assignment, that is using data flow assignments. Reg can be assigned only within these 4 blocks, that is procedural, task, function or user defined primitives. There are other types of register data type, that is integers. Integers declared using keyword integer. Default simulation 32-bit or whichever, if tool has more larger bit, we can take that one. May yield excess hardware if value is not stored in hardware. In such a case, it is good to design a size register. Real means any number which can be declared as a real. It can take decimal value. For example, real delta, if I say integer I, delta is 4.2, then what is I? I will be equal to 4 since I is integer. Integer, real, and this is time. A special time registers is used in Verilog to store simulation time. A time variable is declared with keyword time. Again, the width of this time register will be 64-bit. The system function, suppose there are some system function, if we write $time, that gives us the current simulation time. So one variable, say this same time, is of type time, and initial, if we write $time in this, same underscore time is equal to $time, it gives us the current simulation time. Integer, real and time are not synthesizable. They are just used when we are writing the test bench. They are used for the simulation purpose. Only reg data type in this is the synthesizable data type. Now, when we say array, arrays are followed in Verilog for reg, integer, time, real. There are other type also, real time and vector data type. Arrays, like if I write something as integer count 1 to 5, it has 5 integer. If we write something like reg 7 cross 0, mem 0 to 1023, it says that it has 1024 location. This mem register has total 1024 location. Each location is of 8-bit data. Each location we can store 8-bit data. This say we can take only 5 integer. So now accessing this array elements, if we just write memory 10, we have to write all this 8-bit. It access to that location, and that location has 8-bit data. So if we have to take 1 bit out of it, we need to create one temporary variable, assign this, and then assign the bit to it. So temp2 will be nothing but 0, 1 to 0. So single bit can be accessed from the array, but we have to take one array, one vector of that bit size. Now another data type what we have is parameters, that is used to declare constant, or in Verilog constants can be defined using keyword parameter. So if when we write something called parameter A is like 2 tick B00, we can refer in our entire code as A, B, C, and where A is assigned to 2 tick B00 or 00, 01, 10. Whenever we write digital complex circuit, parameters plays a great role because it helps us to define some constant value that can be read as variable instead of as bits. So parameter reg size 8, now reg size 1, this thing. So we can just change this size and we can change the size of the registers. So parameters are the keyword to declare constants in Verilog. This is about the data types. There are other data types also available, but we are not going through it because it will, like, once you become familiar with Verilog, you can use those data types also. Next is the operators. Logical operators first. Logical is double N. This symbol logical or, logical not, logical or, and they'll compare the values and returns 0, 1 or X. As long as the value is non-zero, it is read as 1. It is logically, we say it is high, true. Only for the 0 value, we say it is 0. So if A is this, B is this. If we write A and B, so A is 6, it is 1, but it is B is, since it is 0, it will be read as 0. So 1 and 0 will always return 0. A and not of B, that is 1. This is again 1. And this, since it is 0, we say it is read as 0, but not of 1. So 1 or 1, this thing 1. C is X. So what it will be? Anything X will always give us X because X is unknown. It is a lack of initialization. So something is not defined properly means it will return X. So an operand not equal to 0 is treated as true. Operand equal to 0 is treated as false condition. Operands evaluated to 1 bit value always, that is, it will give 0, 1 or X. X if any value is X in our design, in our numbers. We have bitwise operators. Again, the operators remains the same. Once you become familiar, these are the same operators as what we use in C, because many of the syntax are borrowed in Verilog from C. It's not like C, but it is borrowed. So the operators are same, but the usage is different. So when we say bitwise operator, it performs this same operation, but bit by bit. For example, I'll say A and B are these value. A is 4 tick B100, B is 4 tick B110. If I write A is equal to this, so not of A means opposite of A. If C is here, it is 10101. If C is A XOR B, so it will take A XOR B here. Then here C is not of A means 0, 1, 1, 0, 0, 1, 1, 0. Here 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1. So this results in 0. Now, here if I say C is equal to A and B, so 1, 0, 1, 0, 1, 1, 0, 0. So 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. So it is performing bit by bit operator. Here if I see one more thing, I didn't tell you, this is A is 2, 4 tick B1010, B is 2 tick B11. So since this is 4 bit, this is 2 bit, it will take the size of the larger operand and 0 will be padded in B. So it will be 0, 1, 1, 1, 1, 0, 0, 0, 0. And these two zeros are extended zeros. Reduction operator, it is performed on a vector and it will result a single bit. Same thing, it is always performed on one operand. So if we say A is equal to 4 tick B100, if I write something as C or of A, it says 1 or with 0, 0 or with 0, 0 or with 1, that results in 1. Again, if any x or z, depending upon the operation, we will get the value. Shift operator, that is defined by 2 arrows this side, 2 arrows towards left side. If it is right side, it is shift right. If it is left, we say it is shift left. Results is same size as the first operand, always 0 is filled. So A is 4 tick B 1 0 1 0. D is A shift right twice. C is A shift left 1. So if we shift A twice right, it will be 0 0 1 0. Always the empty bits will be filled with 0. Left again, so this one will go 0 1 0 0. Relational operators, when used in expression, it terms as again it result 1 means if expression is true, it returns 0 if expression is false. So it is less than, greater than, less than, greater or equal than, less or equal than. It results 1 bit value, that is 0 1 x. If any value is x, it will always result in x. So 1 greater than 0 is always 1, but since there is an x less than 0, it will give x, or z, it will give x. So any operand having x or z will always result in x. X is unknown, lack of initialization. We have equality operators. Equality operators, we have two types. One is logical and the other one is case. Logical means we have this thing, two equals, and this thing not logical inequality. It compares the values and returns 0, 1 or x. In case equality or inequality operator, it compares bit by bit, in even including x and z, and returns 0 or 1. Example, if I write 4 tick B, if this is case logical equality, that is equal 4 tick B. So any operand x or z will return x here. Here also it will return x. But since this is a case equality, the numbers are equals, it will return 1. This is case inequality, so it will return 0. As long as logical means it will return only x if any operand is x or z. Concatenation operator, it used to concatenate the bits. Whenever we want a higher number, we can concatenate two operands to a single number, just putting in this braces, like operands must be size register A. If I put cat x, it is A comma B comma C, means we are concatenating A comma, it should be put in this flower brackets. So it is like A comma B comma C. So 1 0 1 0 1 0 1. Then we have another variable y. So if we are putting B tick comma 2 tick B 1 1 comma A, so B is 0 1 0. Then we have 1 1. Then A is 1, so the value will be read as 0 1 0 1 1 1. Then we have B and 1. This is wrong. Wrong because 1 is nothing but it is in decimal. No size is described, so it will take 32 bit size. So since if it is only 8 bit, it will truncate all the values. So whenever we are concatenating, the operand size should be defined properly, otherwise it will take 32 bit here. Then replication, it is repetitive concatenation of the same number. So if we have to repeat the same number more than once, we'll put it like this and we call that as a replication operator. So if it is 4 in again flower bracket A, B to C. So we are repeating A 4 times, we are repeating C 2 times, D is 1 time. So since A is 1, so 4 times 1 1, B is 0 1 0, so 0 1 0, and then C is 2 times, that is 1 0 1 1 0 1. Then we have another operator in Verilog, that is conditional operator. It says it is represented by a question mark. We say condition expression, if it is true, we say this is evaluated. If it is false, this expression will be evaluated. It always results in 2:1 mux, or whenever we want to have a 2:1 mux inference in hardware, we should design it using conditional operator. So now when we use this cell here, this mux cell is the condition on which the output will depends. Whether output should get A or B depends upon this cell. If cell is 0, we are getting B. If it is 1, we are getting A. So to write it here, we are assigning it to y. The condition expression, as we said here, is nothing but cell. Then we have conditional operator. If it is true, we are getting A. If it is false, we are getting B. So A and B. This kind of expression always results in 2:1 mux in hardware. And on Wednesday, we'll be seeing many design that we are using this way to design so that we can infer 2:1 mux in hardware. Then we have arithmetic operators that says multiply, divide, add, subtract, modulus, and power, exponent. This is same operators what we normally use in other languages. Now we'll start with the various coding style, and that first one is this data flow modeling style. It is also called as continuous assignment style. In continuous assignment statements, it drives the nets continuously. They can be used for modeling basically combinational circuit. Keyword used to design data flow, or in data flow modeling style, the main keyword is assign. So syntax here, it says that assign LHS is equal to some RHS expression. This expression is nothing but some Boolean expression what we are designing in a digital circuit. We can also provide some delay. When we provide some delay, we should write hash delay LHS equal to RHS. Here LHS is always the output. RHS we should have always the input ports. What we are reading, here what we are assigning it. So for example, if we are writing it for a 1-bit adder, here we have used module adder. We have defined ports, that is A, B, some carry. Inputs are A and B, where we are saying that A and B are inputs. And here we will say that sum and carry are the output. Here we are using assignment and we are using arithmetic operator plus. So carry and sum, since A and plus B will give us 5 more than sum and carry both together. So we are concatenation. Concatenation operator can be used both on the left hand side and the right hand side. And we give delay of 5. Delay, if it is there in the design, it is optional. If it is not there, we'll just skip that delay part. So in concatenation operator, we wrote carry comma sum and A plus B. So if A plus B, the first bits will go to sum and the last MSB will go to carry. So this is nothing but the data flow modeling style. Same way we can even write it like assign carry is equal to, we have equation that is A dot B, sum is equal to assign sum A XOR B. That is also one way to define the 1-bit adder, or that is half adder. Now we have behavioral modeling style. When we design digital circuit, writing Boolean expression becomes difficult. It is not that easy to write a Boolean expression for all the circuits. So we need to define the functionality in an algorithmic way. And when we define, we know the algorithm, we should how to code it in Verilog. It is the behavioral style we should follow when we are having an algorithmic knowledge of the design. So in the behavioral modeling now, the key statements are initial and always. These blocks contain series of statements. Again, these two blocks are a concurrent blocks, but the statements written inside these blocks can be executed sequentially or parallelly. All blocks in module operate simultaneously, that is concurrent, but the statement written sequential or parallel operation within these blocks are possible. The statement written inside these blocks can be operated sequentially or parallelly. Whatever outputs are assigned inside this initial or always should be of type reg. That's what the left hand side of assignments are always variables, and that is of type reg. Now initial block execute only once. It starts at time 0. Usually cannot be synthesized, and hence it is useful for writing test benches. Test benches is nothing but it's a wrapper around a design through which we will force the stimuli and or we are giving the inputs to the design and evaluate the response of the design. So this initial blocks are widely used in writing the test benches, can provide initial. So using inside this use in test bench, we can use the initial blocks to initialize memories or flip-flop, often used to reset the signals. Inappropriate for combinational logic, it usually cannot be synthesized. That's why used for the simulation purpose. Now, if a procedural block contains more than one statement, those statements must be enclosed within begin and end or fork and join. If we want sequential execution, put begin and end. If we want parallel execution of the statement, we'll put fork and join. So begin and end, fork and join group several statements together, but begin and end cause the statement to be evaluated in sequence, delay in the sequence accumulated. But fork and join cause the statements to be evaluated in parallel, and timing within the parallel block is absolute to the beginning of this group. For example, if we write initial begin, there are clock reset enable data. Here also we are giving clock reset enable data. We are assigning 0, 0, 0 to all, but the timing given inside begin and end is #1. So clock at 1 unit of time will be 0. Reset will be 0 at 6. It will add the delay. It is in sequential nature. So at 6 unit of time, reset will be 0. 6 plus 5, 11. Enable will be 0. 11 plus 2, 13. And data will be 0. But here, 1 clock will be 0, at 2 data will be 0, 5 and 5 both reset and enable will be 0. It is absolute. So timings in this are absolute to the beginning. All the blocks will start at time 0. Whether this block, this all block starts at time 0, but here the delays are additive. Here it is absolute to the beginning of this block. Then we have, so begin, so as what we discussed, get 0 and it is 13 units, but here it is at the same time 1, 2 and both will be getting data 0 at 5 units of time. Then we have always block that operates continuously on or on a trigger list to, so since it operates continuously, we can't use for synthesizing purpose. That's why it is used, it is controlled using a trigger list, and that trigger list is nothing but followed by a controller operator followed by all the inputs of our design. It cannot be used with the initial block, cannot nest initial or always, but it can be used in the same block. This is a very basic example to use both initial, always, and this example also shows how we can generate clock, that is how to do the clock generation in test benches. Here we will declare clock as reg. Then we will initialize, since initial block execute only once, we have initialized it to 0. And then always blocks operates continuously, so it is always #10 clock. So this will give a clock of time period 20. This is nothing but a clock, that is a time period 20. So #10 it is 0, then it will become, after #10 again it will be 1. First it is 0, then 10 it will be 1, then again 20 it will be 0, 30 it will be 1, 40 it will be 0. So it is nothing but it is generating clock of time period 20. And this is one way where we can use both initial and always together. But in this always, if we see, it is operates continuously, there is no control. But same way, we cannot use this always block for the design purpose. That's why we are using it with one control operation, that is @ followed by the trigger list. Now, conditionally execute inside of always block continuously operating. If trigger list present, continuously checking triggers. So any change in any of this trigger list will infer or will trigger this always block, always at #a bar @a, b, c, begin and end. We can even write a x1 or x2 or x3, that is a or b or c, or we can use Verilog. It depends upon the updations of Verilog, because we said that it is IEEE standard, that is 1364, which has got approved as standard in 1995, then it got updated in 2001, 2005. So before this trigger list, we have to use this event control operator with the trigger list. When net or variable in trigger list changes, always block is trigger. So original way in from 2001, we are using, instead of or, we are using x1 or x2 or x3. So always at, suppose we are writing it for 2:1 marks. So we have two inputs, in 1 and in 0 cell. So we wrote always at in 1 in 0 cell. Begin, if cell is equal to 0, it is 0, else it is 1. So this says that whenever input 1 changes, input 0 changes, or cell changes, this always block will get executed and it will update the output. The other one is always at ABC. So we are assigning begin. Whenever we have more than one statement inside always block, we should write it inside begin and end. So if it is begin, A1 is this, A2 is this, A3, and carry is this. So carry is A1 or A2 or A3. So whenever there is a change in ABC, A1, A2, A3 as well as carry is updated. Now, when we talk about procedural blocks, in procedural block, that is initial and always, we can use two types of assignment. One is equal to, one is less than equal to. It is not the relational operator here. It is something called as non-blocking assignments. These assignments are used to assign only a rich integer, real, or the time data type, because they can assign only inside the procedural block, and procedural block supports these types of assignments. Now there is a difference between when to use blocking and when not to use non-blocking. So blocking is assignment is specified by the operator equal. It is evaluated sequentially. It means whenever this is insert, it will execute and update the left hand side variable and then go to the next statement. That is why it is evaluated sequentially, works most what we do in our software languages. This operator is mostly used to design combinational circuits. For example, if I write something like word, this is the 8 bits I have taken, 7:0, or I'll just write A comma B, B comma A. So does this perform a swapping operation? No, because it will update. It is like a sequential thing. So 7 A, if I write this as A, this as B, it will update. So both will have the same value. It will not perform the swapping operation. But same time, non-blocking assignment specified by this operator less than equal to, all the statements within sequential are executed parallelly, concurrently. It will update, it will execute, but updation will happen at the end. Updations will happen simultaneously if no delay is given. If delay is also given, updations will happen at the end, but with delays. So it is word 15:8 if I take as A, word 7:0 is if I take as B, it is A assigned to B and B assigned to A. So it will update it, but it will execute it, but the updation will not happen. So here the swapping operation will take place. So A will get B value and B will get the A value. Similarly, if I give one more example, it is, we have taken an 8-bit registers here. If A is equal to B plus C, B is A plus D, A plus B, D is A, B plus D, assume if it is 1, 2, 3, 4, what will be the value of A, B, C, D? Here, if we see here, A is, so it will be B plus C, 2 plus 3. So A will be 5. So next value when we calculate B, A will no longer be 1, but it will take 5. So it will be 5 plus 4, 9. So now B is updated to 9. So now it will be 5 plus 9, 14. C is updated to 14. So similarly, D will be updated. Here, if I say B plus C, so A is executed to be assigned to 2 plus 3, that is 5, but it is not yet updated. Updation will happen. All A, B, C, D will be happening together. It will happen at the end. So A will be 2 plus 3, 5, but B, here A value will be still 1. So it will be 1 plus 4, 5. A, again A plus B, so it is 1 plus 2, 3. B plus D means 2 plus 4, 6. So all this will be updated together. Here, updation and execution will happen together. So shouldn't use blocking with sequential because it doesn't give always the correct result because updation happens together. So now, yes, it can work, but this model's pipeline stages are better. You can use problems if multiple always block. Order of statement is important with blocking assignment. Some guidelines, non-blockings are used for sequential, blocking is used for combinational. Don't mix it in the same block. So this is just a guidelines. We can use non-blocking for combinational or blocking for sequential, but a not basic guideline says that we should use it this way. It will always give us proper result, because when we go order, we'll get a different hardware. Now when we discuss about this behavioral modeling, here one more thing comes: how to design a sequential circuit. Sequential circuit means how to infer a flop in hardware. Flop is nothing but whenever a output input is transferred to output when there is a positive or negative edge on the clock. In Verilog, the positive or negative edge is recognized using the keyword passage of clock. So we'll make that always block. The previous one always block, what we have seen, is always at the rate a comma checking whether they are changing from 0 to 1 or 1 to 0. That is level sensitive. But here this always block at the rate passage of clock. It always says if clock change from 0 to 1, x to 1, it will never be anything else. It is always, this always block will always trigger whenever there is a clock 0 to, there is a positive edge on a clock that is from 0 to 1. And then we are assigning input to output. And whenever this type of assignment is there in our digitals, in our coding, we are inferring a D flip-flop in hardware. When we have conditional operator, we infer a mux. When we have this kind of operator, we infer a D flip in a hardware. Then we have combinational versus sequential. Combinational, as we say, not edge trigger. All inputs are triggering, does not depend on clock. Edge triggers by clock signal. Only clock appears in the triggers. Can include combinational that feeds a flip-flop. We can have some combinational circuit, but inside in the trigger list, we'll have only clock or some asynchronous signals. Inside behavioral modeling, we will use some conditional statements. These are also called as sequential statements, are supported by behavioral modeling, and in that the one is the if else statement. It will check the condition and then the flow of this program will be there. If else statement controls the executions of other statement. If else controls the flow of program. So if condition is true, we'll follow this statement, else we'll follow this statement. If we have more than one condition, if condition statement, else if condition statement, else statement. Again, if we have more than one statement to be executed for one condition, we can put it inside begin and end. If we have only one, we can skip begin and end. Here also the same logic. If we have more than one statement or one assignment to be performed under true condition, we can put it begin and end. Otherwise, we can skip begin and end. Else should be there, otherwise it will infer a latch in hardware. So for example, one comparator design, here we have two inputs A and B, that is a 4-bit each, and we have three outputs, A less than B, A greater than B, A equal B. So we have declared all the ports here, A and B, A less than B, A greater than B, A equal B, and when we have a A and B as the input, that is 4-bit each. Now, since the assignment inside the procedural block should be of type reg, the output should be declared as reg type here. Otherwise, it will give an error. It will not supported by this always block. So always at A or B begin. If A is less than B, we say A less than B is equal to 1, else all will be 0. So if A less than B, begin, since we have more than one statement to be written inside this if statement, we'll write begin and end. A less than B1, A greater than B0, A equal to B0. Else if A greater than B, begin A less than B0, A greater than B1, A equal B0. Else A less than B0, A greater than A equal to B1. So like that we should write it. This is more than one if, else if, else, last condition. And begin and end for everything. Begin, end. This begin and this end. This one and this one can be skipped because there is only one if statement. We can write it, but even we can skip this begin and end. This was a combinational circuit. A and B are level sensitive. Now we have to write a code for D flip-flop. So module D flip-flop output reg Q. Now here port type and port declaration is happening together. Here port type and port declaration was differently. So if we say type here, output, since again we are using the procedural block, we have declared this as reg input D input clock. Always at passage of clock begin. Q is assigned to D. Again here we have taken care of writing a non-blocking since it's a sequential, and here we are using the blocking. So it is always at passage of clock we'll write Q is assigned to D. There is no else for this statement, or there is no if also. I didn't write this thing reset, so it is just directly always at passage Q is assigned to D. So it is like just a one D flip-flop. In the second thing, D flip-flop with reset, again we have ports as Q, D, clock and reset, where Q is the output, clock, reset and D are the input. Clock and reset are the controlling signals, D is the assigning signal input, where clock is the synchronizing main thing. So we are writing always at passage of clock. Here if reset is 1, we are saying that Q, else Q is 0. But Q should be declared as reg type. So even we can write if reset is 1, Q is 0, else Q is D. So it makes active low or active high reset, and it is the synchronous D flip-flop. Now we even have asynchronous and synchronous reset. There are, when we design flip-flop, we design with the synchronous inputs, we design with some asynchronous input. Synchronous input says that they are in sync with clock. Only when clock is active, we will check that, and then we will assign the other inputs, or the inputs at the D flip-flop will go to the output. But asynchronous inputs has their own priority. Whenever they are active, they will be ruling the output irrespective of the clock. So if I say module D flip-flop synchronous output reg, same thing, D clock reset, always at passage begin. If reset is 1, Q is 0, else this. So this reset doesn't has its own priority. It will check whether clock is active or not. Only after that we will check whether reset. So this reset is in sync with clock. It's a synchronous reset. Then we will go for asynchronous. It is also triggered by a reset signal. Even it means that always block should be active when the reset is active, not only when the clock is active. So your always block, here again module name, output reg Q, input D clock reset enable, always at passage clock and passage of reset. And means passage of clock, comma, or passage of reset. In the previous example, passage of reset was missing. Here we are adding it. Now here we can check why we are checking with passage of reset. We can only write reset. We can, the Verilog supports this syntax, but synthesis tool will not support this syntax. If one input, one trigger list is edge trigger, the other one should also be an edge trigger. Either we should have all H trigger signals or we should have only level triggers. We cannot mix the H and level trigger signal in our trigger list. Since we are having passage, we need the assignment to happen at the passage of clock. We want, when we are adding a synchronous reset, that also we should attach to the edge. So we are adding passage of reset begin. If reset, this is making it as active high. If reset is 1, Q is assigned to 0, else if Q is assigned to D. If enable is 1. Even though we are putting passage of reset here, but since we are checking the condition, we are making it enable, we are putting this reset here. That checking of reset will make that signal as a level signal. It is not the synchronizing signal. So synthesis tool will understand what is last assignment, else if enable is 1, will happen at the passage of clock, not this one will happen at the passage of clock. So this is the difference between synchronous and asynchronous signals or the inputs when we are designing a D flip-flop. One example of counter, module, again counter, input. This all codes we are running on Wednesday on model sims. Module, counter, input. We have 3-bit and 4-bit input. Then we have clock, reset, load, up and down. And then we have output as 4-bit again. So we are designing an up-down counter that can count up, that can count down. So since we are designing up-down counter, we should control the counting through the pin load, and even we can load the counter from our input. So for that we are using one load pin. Always at passage of clock, if reset is 1, first input always will be reset. We'll assign everything to 0. Again, see, this is the number representation, 4 binary base, and this is, then 0 is missing. I'll just add it, 0 0 0 0. Then else if load is 1, Q should be assigned to DI, so Q is assigned to DI. Else if up and down, if it is 1, we are putting as +1, otherwise it is -1. So it is +1 and this is -1. This code in more detail, we will see it on Wednesday. Then we have another statement called as conditional statement. Again, it's a sequential statement case. The case statement compares an expression to a series of case. And if we were going one by one, it will follow the flow. Here it will compare this expression in a series together and execute the statement or a group of statement with the first matching case. Case statement supports again single or multiple. Group multiple, if we have more than one statement, put it using begin and end. So we have case, expression, case 1, colon, statement. If this expression is equal to case 1, the statement executes at this. Expression equal to case 2, execute this statement. Default will be these statements and end case. Since it is starting, we have to end this using end case. So now default is must. Again, in this case, the part of the syntax itself. So we'll be writing it in this way. For example, multiplexer. Here we take module, module name. Again, we have declared the ports, that is out, I0, I1, I2, I3, and then we have 2 select lines. Since it's a 4:1 mux, we have 4 inputs, 1 output, 2 select lines. So we have taken the ports that way. Now we are declaring the type. So output will be out. Then we have input I0, I1, I2, I3, and then we have select lines S1 and S0. Since we are using the procedural blocks, again we are declaring this out as reg, and always at inputs are, again we'll put all the inputs inside a trigger list. So inputs is select lines are also inputs. So S1, S0, I0, I1, I2, I3. Now we have to check what is matching with this select line. This is the controlling element I0, I1, I. If these two are 0, 0, I0 should go to out. If this is 0, 1, I1, if 1, 0, I2, 1, 1, I3. So that's why we have put the concat, since it is 1, 1 bit, we have put the concatenation operator on S1 and S0. And then selection line, this is the case syntax. It should be in the round bracket, that expression. So we have put that round brackets. If that is equal to 0, we'll assign I0. If that is equal to 1, we'll assign 1. If it is 2, 2, 3, 3. Default, we'll say it is an invalid control signal and we'll end case and end module. This will to 1 mux. Then we have case Z and case X. These are the special version of case statements allow X and Z logic values to be used as 1 second. I'll just 1 minute. Okay. Then we have special version of the case statement, that is case X and case Z. Case Z uses the Z as don't care, whereas case X uses either X or Z as the don't care instead of logic values. Example, one is the 8:3 priority encoder. Here we are writing a module. We have encoder. Inputs are, we have 8-bit input, that is A in. We have one enable input and 3-bit output. So in this enable is 1 bit. So we have declared it as input. Then we have 8-bit. So we have used input 8-bit vector 7:20 to define A in. And we have 3-bit output, that is output 2:0 Y out. Then since again we are using the procedural block, we are declaring it using, as we are declaring this as reg, always at en or en. Again, it's a combinational circuit, so our always block should trigger on both the inputs when it changes. So we included both the inputs in our trigger list. Begin, if enable is not equal, when we write something like this, we are saying that if enable is not equal to 0, it's true condition, we'll put as 0. So if it is not, we will say that case X or A in. It says that case X, it will treat X as don't care. So if it is 0, 0, 1, if this is 1, we are putting 0. Otherwise, if this is, it can be anything 0 or 1, then this is 1 means we are putting 0, 0, 1. So this code will give the priority to the LSB. Only if LSB is 0 or 1, we will check that next bit. If both bits are 0 or 1, we will treat this as 1. Instead of case X, if we just write case here, it will give error because it will not read X as don't care. Even if I write case Z, I cannot read X as don't care. That time it should be written as Z. But case X will read both X and Z. So even though if I'm writing X here, if I write Z, it will be giving me the same results. So here X is treated as don't care, and depending this all last bit, it can be anything that is 0 or 1. But if last bit is 1, we are getting 3 tick B11. So this is nothing but the 8:3 and priority encoder with priority given to LSB bit. That is to A in 0, A in 0 to A in 7. Then in Verilog, we have again one more type of sequential statement available, that is loop statement. Loop statement appear inside the procedural block only. We have 4 looping statement, forever, repeat, while and for. To start with for, the for loop is the same for loop used in other programming. It starts with for initial assignments, expression, step in assignment. Initial assignment, once it is executed once in the beginning when the loop is starting. Execute the loop, then the loop will be executed as long as the expression evaluates to true. Execute step assignment at the end of each pass through the loop. Example, we have integer count initial. It should be, again, since it's a sequential, it should be used inside procedural block, and it should be, the assignment should be a variable type. So count itself, integer is the variable data type, so it can be used. So for count equal to 0, count less than 128, so count is then count plus 1. So this is initialization, this is expression to be evaluated, and this is the step assignment of plus 1. So what we have to display? Count %d, and we are displaying count. So initially count is 0. Since count is less than 128, it will display it. then 0 plus 1, it will display 1, then 2, 3, 4. So last value what it will display is 127, 128, it will come down. So it will display from 0 to 127. Then we have while loop. The while loop execute as long as expression evaluates true. Same thing, while, expression, and then statements here. So as long as this expression is true, we will evaluate the statement. It can have a single statement or multiple statement. If we have more than one statement, we have to put it inside the begin and end. Example, same example of count. So we have declared integer count. Again, initial, we have initialized count to 0. While count is less than 128, display count. So since it is 0, we will display 0. Then it is, since it is less than, it is true, count is plus 1. So it will keep repeating as long as it is 127. So it will, count is 127, exit the count at 128. So it will display again from 0 to 127. While and for loop, as if we can write this, you can write this, it is same thing. It is just the same example using both for and while. Then we have repeat. The repeat execute the statement fixed number of times. So if we write repeat 128, it is same way, count 0, repeat 128, begin. Count is equal to percentage d count. So it will again display and count plus 1. So it will keep repeating it at 128 times. So it will display from 0 to 127 again. Then we have forever loop that executes continuously. The loop never ends till we finish it explicitly. So now reg clock. This is one way to generate clock. The other way is using initial always. This is another way to generate the clock, where we write reg as clock initial begin. Initialize to 0, it will execute once. And then since initial block execute once starts at time 0, both are at 0. So initially 0, but forever, but it will give a delay of 10. So initialize to 0, then after a delay of 10, we are giving clock as not of clock. So it will again generate clock with period of 20 time unit. Same using initial and always. So this is about the behavioral modeling. Behavioral modeling, where we define the functionality of the design in terms of some algorithm. For that, we use two procedural blocks, that is initial, always. Initial is used for simulation purpose, always is used for design purpose. Again, when we use always block, we should use it with some controlling operators. Inside always block, we can use two types of operator to assign, that is blocking, non-blocking. But all the assignment, all the LHS should be of type reg. Blocking, non-blocking has its own definition. Blocking should be used as a combinational in combinational design. Non-blocking should be used in sequential, should not mix the style. Then we have three sequential statements that can be used inside the behavioral modeling, or that can be used inside procedural or behavioral modeling style, that is if, case, and loop. Then the other modeling style, what we have to discuss, is the structural modeling style, where we build the design from the gate, flip-flop, or the latch level. Flip-flop actually constructed using behavior. Verilog provides a set of gate primitives as AND, NAND, OR, XOR, XNOR, NOT, buff if one, and etc. Combinational building block for structural design, we have the known behavior, and we can also model at the level. We can model it at the transistor level using the switches. Now primitives, no declare, we don't want any declaration to be done for the primitives. They are inbuilt, available in Verilog, can only be instantiated. Whenever we call primitives, it should be called by the keyword and, NAND, NOR. In this, always the output port should be appear same code, we have even used the data flow. So depending upon our wish or depending upon the types of design we are doing, we can mix the style of both. Mix the style means mix the data flow, behavioral and structural. One more example is of 4:1 mux. You will have, this is the design. Out is equal to I naught, S1 naught of S1. When S1 is 0, S0 is 0, we have I0. When S1 is 0, S naught is 1, we have I1. When S1 is 1, S naught is 0, that is 1, 0, I2. Both are 1, we have I3. So this is the structure for that. And same thing using the primitives. So out we have.
Ma'am, the PPT is not visible.
What? Hello, I can't hear you. One second.
Ma'am, the PPT is not visible.
It's not visible. Sorry, I didn't. From when it was not visible? Just now or till now? One second.
Last one was primitives.
Last, just now, from 4:1 marks, correct?
Primitives.
This was visible?
No, primitives. The last heading was something like primitives.
Last reading was the primitives. I was saying here.
Yeah, this one, yeah.
Oh, after that it was not visible?
No, after that the connection was not there.
Okay, connection was lost from my side, correct? It's okay, sorry. Do you want me to repeat this, correct? Syntax for structural Verilog?
Yes.
Okay, so we were discussing about primitives. Now we will start with the syntax of structural Verilog. When we design structural Verilog, we can even call the lower modules or the primitives. Primitives already we saw how to call, but we can even call the lower modules. Lower modules are called using module name, followed by instance name, followed by port mapping. Port mapping means mapping of the lower level module ports to an upper level module where we are calling it. All internal wires here, we will declare it using wire. The instantiate the primitives or the submodules. We can instantiate either the primitives or the submodules in the same module. Now we just will take an example here. This is an example of 1-bit full adder designed using half adder. Here we use one half adder. This is one consists of one XOR gate and one AND gate. A and B are the inputs, S1 and C1 are the outputs of half adder. Then we are using one more half adder, that is another XOR gate and AND gate, where the input is S1 and Cin, but the output is sum and H2. And then there is one extra. This should be actually OR gate. By mistake, it came as XOR. It should be OR, where the input is H2 and C1 to this OR gate. Now, when first we should code this lower level module. So this is done using procedural block, that is behavioral modeling. So we gave module and half adder. The ports are Cout, sum, A, B. Here we gave output reg, sum and Cout, inputs A, B, always at A and B inputs. Sum is assigned to A XOR B, Cout is assigned to A and B. This is what is the half adder design, and this is done using behavioral modeling style. Then we have to design it using the 1-bit full adder using structural modeling. So we have to call the lower level module that is already built half addered. Then we have output. 1-bit full adder has two outputs, sum and Cout, three inputs A, B, Cin, already seen here, and we have three intermediate signal S1, C1 and S2. That is declared as wire. Now, as we said, lower level modules are called by module name. So it is called by this module name, followed by instance name, followed by the port mapping. So port sum should be mapped to S1, Cout is mapped to C1, A is mapped to A, B is mapped to B. So sum is mapped to S1, Cout is mapped to C1, A is to A, B is to B. Then we call one more times half adder, same thing, module name, but the instance name should be different. Here we cannot write AH1 and AH1 together because this is separate, this is different. Input and output of this port is different. So we are writing AH2. Now here sum is mapped to sum, Cout is mapped to S2, A is mapped to S1, and B is mapped to Cn. So sum is mapped to sum, Cout is mapped to S2, A is to Cn, and B is to S1. Then we have Cout. This is, as I said, it is OR gate. So it is H2 or C1. Even we can call here primitive, that is C1, Cout, comma, H2, comma, C1. So this example will give you, first it will show us the structural here. This line will give us data flow, and this part will give us behavior. It says that we can mix all the three styles for writing this one design. It's not necessary that if you follow structural, you should follow structural. As already discussed in morning, we follow normally top to bottom and top to down and bottom to up approach. So when we do those design methodology, when we follow those approaches, any design style you can take it where whichever is more easy or whichever is feasible to write that particular design code. Thinking about the hardware. First you should think hardware and then you should design the style. After that, one more example what we took is of mux. That mux says output. It says when it is 0, 0, the output is I0 is nothing but goes to output, or output is equal to I0. When it is 0, 1, output is equal to I1. When it is 1, 0, it is I2. When it is 1, 1, it is I3. So depending upon these structures, we will just code it again using our structural modeling. Here we have two intermediate signal this way, and Y0, Y1, Y2, Y3 are another four intermediate signals. So we have taken wire S1, not of S1, S0. See, again, the names of the port, they are self-descriptive. They represent what signal it represents. So it says wire S1 not. So it is nothing but when we are putting not of S1, this wire. S0, not of S0. Then we have four output, that is Y0, Y1, Y2, Y3. That is the four output of four AND gates. So then inputs and main output is here. So now when we write not of S1, S1 is this not, one more NOT gate, S0 N is equal to comma S0. So S0 N is the output, here S1 N is the output of the NOT gate. Then we call one AND gate. So here it will be the output is Y0, it is I0, S1 not, S0 N. So it is Y0, I0, S1 not S1. Then we call Y1. So we'll call one more AND gate. Here it will be I1. Then we have S1 not and S0. S1 not and S0. Similarly, we will call one more Y2, Y3, and then we will call one 4 input OR gate. So main output followed by Y0, Y1, Y2, Y3. That are the four outputs of this AND gate. Here Y0, Y1, Y2, Y3 should be of type wire. They should not be of type reg. Similar, this is one more example, but it is with delay. As we already discussed this delay, it is just delay of 5 gate at E1, and this will generate delay of 4 units at output. So total delay at out will be 9 units. Now this is the basic style of various modeling style in Verilog. Other than that, that is gate level modeling using primitives, then calling structure, calling lower level modules, both come in structural. Then we have behavioral, data flow, behavioral where we are defining functionality, data flow where we are defining the flow of data or input from data from inputs to output in terms of Boolean equation. Other than these three style, one more style is that switch level where we call directly the transistor, and that transistor level is the lowest level of abstraction to describe the digital circuit. But most of the time we do the modeling at the gate or the RTL level. And behavioral. So now to end, this is what about the coding styles. Now there is one more thing to how to design a complete digital circuit. We understood the style. Now we have to just complete the digital circuit so that you can design it for any application. All your digital system is divided into two parts. One is the data path unit and the other one is the control unit. Data path unit actually is called as the execution, where the data, where this operation on the data happens, the manipulation of the data happens. and that manipulation or the execution or the operation depends upon the signals generated by the control unit. So we have two parts, control unit and execution. Execution unit, we can design the way what we discussed previously, that is either using behavioral, structural or data flow, but control units are designed using FSM so that we can define the sequence of operations. So here execution unit provides all necessary resources and interconnects among them to perform specified tasks. Examples of resources are adders, multiplier, registers, memories, etc. Control unit that controls the data movements in an operational circuit by switching multiplexer or enabling or disabling the resources. Follow some program or schedule, and this is implemented using finite state machine, or we call it as a collection of finite state machines. Any circuit, now what is FSM? Any circuit with memory is a finite state machine. Even computers can be viewed as huge FSMs. Design of FSMs involves defining states, the transitions between states, and their optimization or minimization. This approach is practical for only small FSMs. Now, there are two types of FSMs. When we have some, when we talk about FSM, we basically talk either of Moore FSM or Mealy FSM. In Moore FSM, output is function of the present state. Here the Moore FSM, if I say, as we said, it consists of the states. So it consists of the states and the output function. Here, the inputs and the present state. What is our current state? For example, if we go and see a traffic light controller, the current state is 30. Depending upon the current state 30, we say the next state is 29 if it is a down state, down counter. Then if we say the current state is 29, the next state will be 28. There is no extra input. Sometimes the inputs may be there, but in this traffic light, we don't have any extra input. So automatically it goes. So depending upon the current states, we have the next state. So this says inputs and the present state, it will define the next state. That next state, as soon as the clock will come, will become the present state. And again, depending upon the present state, we have the output. So there the output says the green light is on. So this is what we, when we have any controlling, when we have fixed sequence of operation, we define it using the finite state machine. In that, Moore FSM says that the output function depends upon only the present state. So present state says that if we are from 30 to 0, the output is green. Red is off. That's what it says. Then we have the transitions will happen here. This is a representation of the Moore machine. We have state 1. Suppose we have two state. We'll go from state 1 to state 2 with output 1. Whichever output is there in that particular state, that is asserted, that is active. We have two outputs, suppose here. So in state 1, output 1 is high. If output 2 is not written, means output 2 is 0. When we come to state 2, we say output 1 is 0 and output 2 is high. Transition condition 1 will says that we are going from state 1 to state 2, and this says that transition condition 2 is the condition which will make us move from state 2 to state 1. Then we have Mealy FSM. Everything remains the same. Only if the output function depends upon the present state as well as the input. In the Moore FSM, output function was only the dependence on the present state. There is no dependency on the inputs. But here we depend on the present as well as on the input. Next, and here next state function is again on the present state as well as the input. We'll find the next state. This next state, when the clock will come, will become the present state. So once this present state inputs, we'll have the output. Then Mealy FSM, again we have state 1, state 2. If we see the difference, there's state 1 with output 1, state 2 with output 2. Here we are going from state 1 to state 2 when this condition is true with this output 1 asserted. When we say this output 1 is there, means we are making this output 1 active. Similarly, we'll go from state 2, state 1 when this condition is true but with output 2. So Moore FSM, with state, we are activating the output, but in Mealy FSM, with state as well as with this condition, we are making one particular output to be asserted. So now when we say FSM, it is very easy to code the Verilogs FSMs in Verilog. here if we see, we have 3 blocks: next state, present state, and output. This present state register is nothing but one always block, which is a clocked always block that is triggered on the passage or the negage of clock. And then these 2 blocks, that is next state function and output function, can again be written using always block, but they'll be combinational block. Similarly, here also we have 3 always block. This present state register will be the clocked always block, next state function, and output function will be another 2 procedural block, but it will be only the combinational always block. So same it is sensitive to clock and asynchronous reset. Output and next can be described in another 2%. Then one more thing, when we do the codings, we have to assign the states, that is states encoding. And that is how, well, suppose we have only 2 states, S0, how to give them, or suppose we have 5 states, S0 to S4, how to code them. So encoding depends upon, basic is binary, you say S0 is 000011 2 3 4 like that. But there is another style, that is one hot and gray encoding, that is used basically when we want low power designs. So one hot means we'll have only one bit active at a time, all other bits are 0. So suppose if we have 6 states, we need 6 bit to do the encoding, that is 000001. S1 will be 000 010. Like that, we'll go till X6. Binary means, again, if we have 6 states, we need only 3 bits because it will vary from 00 to 110. And gray means it will be in the gray coding, where only 1 bit transition will happening from one state to another. One hot and gray coding styles we normally prefer when we go for low power design. And that is what binary is used when we need some simple, when the power is not an constant for you, you can go for some basic thing, that is binary. Otherwise it has to be go for. But gray encoding we normally prefer because it gives us low power also, and it is simpler, it takes less number of bits also hardware wise, because in one encoding the number of bits will be more, it will take more register to store that. So most of the time we'll prefer gray coding style. It reduces the power, it will take the less number of bits to store that. So this is all about FSM. Wednesday we have a hands-on with you. So whatever we have seen, we have not gone in the example for all the styles, including FSM. We have some codes with us. So we'll be explaining those codes. All the basics are given to you today. We'll be explaining and running the same codes using the model sim. And we'll be starting with the 2:1, that is the basic element to design all other designs for us. And thank you. Any questions from your side? Is there any questions from your side? You can write in the chat box. Is there any question? Should we? I'll just to Suma ma'am now. If any question, please let me know. Otherwise, thank you all. I am here in the session, but if any question, please do let me know.
Hello, we are open for questions. Otherwise, Wednesday also we will be continuing with the same session, but we will not touch upon the basics. We will go, I think the day morning only we will start with the coding. But the thing is, everything will be realized using 2:1 box. The reason being, as all of us know, everything will be in the form of 2:1. The reason being, all FPGAs internal structure can be realized in terms of 2:1. Like each of these FPGAs or LUTs based, that is lookup tables will be in the form of 3:1, and hence we'll be sharing with you all how to realize any of the combo logic or the sequential logic using the 3:1 multiplexers. And as we explained, gate level modeling and data flow modeling is not applicable that much for sequential design, as it is continuous and it will be active every time. And because of this drawback, we are going for behavioral modeling, which is user friendly, and any algorithm can be directly implemented using behavioral model. So we'll be starting directly with hands-on on Wednesday. I think I already shared to Jalja madam, uploaded the model sim. So we'll be doing the hands-on on Wednesday, and tomorrow we'll be having biomaterials, which is very important for medical devices. And afternoon we'll be having the physical design on 3D ICs. That's all for today. If you have any queries, we are open to that. Can we quit, madam? Hello?
ಮ್ಯಾಮ್ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
Hello?
ಹಲೋ,
ಕೇಳಿಸ್ತಾ ಇದೆ, ಹೇಳಿ ಮೇಡಮ್.
once again we'll start at 10 o'clock, no, ma'am?
10 o'clock ಅಥವಾ 11:30? No, I'll just check the schedule. Wednesday. Yes, madam.
The first talk will be Chetan Singh, then followed by 11:30 is your session.
So 11:30 to 1, alla madam?
Yes, ma'am.
Yes, madam. That's what 11:30 to 1 is biomaterials, and 2 to 4 it is on 3D IC.
Yeah.
Okay, both online. Yeah, both online. That okay. That is what it's ready, madam. Tuesday, not an issue. Tomorrow.
Okay, you told you to share the drive, no, ma'am?
Yes, madam. I think I told the other student. I think she has uploaded, I think.
Okay.
Please check it. If it is not there, once again I'll resend.
Okay.
Okay, along with the setup file, it is sent, madam. If not, again I will resend.
Okay. Thank you, ma'am. Thank you very much for today's session.
Yeah, thank you so much. Thank you all.
Madam, can we get other PPTs?
Which others, madam?
Other sessions PPTs.
Yeah, today's we can share.
No, not today's, madam. The earlier one, the one on MEM resistor and remote computing and all.
Madam, I think Dr. Jalja will answer, I think, for this.
Yeah, still I have not received any speaker presentation. Once if I receive, I will WhatsApp you. Thank you, everyone. We'll once again meet tomorrow at 10 o'clock. Thank you.
Otherwise, even the session recordings also okay, madam. If it is available.
Madam, today's session, I don't think you'll have any issues, because on Wednesday we'll be having the hands-on of the same thing what was told today.
No, not today's, madam. I'm asking Saturdays. You also told earlier that Python programming we have actually learning, machine learning, deep learning, CNN, all that we have. But this thing is Saturday session.